let me just start talking a little bit about the agenda for today. Good morning, everybody who's here so far, and I see that the attendees continuing to climb. Today is day 3 of the ASO workshop for this year, and again, we were really hoping to have the workshop in person, and we had thought for a little while that we were going to do it, and then Delta raised its ugly head, and we concluded a ways back that it was probably best to keep it online this year. But we're really hoping next year to be in person. And I know Joe Boardman is especially excited by the idea of getting to ride up and down on the gondola again, while the closing party is going on up at the summit. So today we are starting out with a keynote from Steve Haugen. We're really excited about that, and I'll give an introduction to Steve here in a moment. And then our speaker session starts after the break at 10 o'clock. Although I told Steve if he feels motivated to keep on talking a while, we can cut into lunch and cut into break. But at 10 o'clock, we're going to have a talk between Jacob Wasilkowski from ESRI and our own Evan Burgess about the ASO web development progress that's been going on. And then Arielle Koshkin from UNR, grad student there. Ann Nolan spoke about her work the other day with the creek fire and the work they've been doing in the creek fire. Reggie Walters from Hetchy, Water and Power, and Reggie's part of that crew that in the Tuolumne that we first worked with. So our first flights were in the Tuolumne back in 2013. And so they've been able to take advantage of the years when we were having 10 flights per year, and to really lay in the foundational empirical model, as well as constraining their PRMS model. So looking forward to seeing what they have this year. And then HP Marshall, who's at Boise State, is going to talk about the Airborne L-band synthetic aperture radar, interferometric SAR data, and the ASO lidar in the context of the SNOW-X activity with NASA. Marco Bell is going to talk about the HMS model that is being built, and he's bringing the whole community of the San Joaquin together on that. And then finally, Greg Stock from Yosemite will give an update on the historical ice volumes of the Lyell and the Maclure glaciers. And we've been updating those data sets, and so we're of course really excited to see that. And Greg is the one that finished out that map of the last glacial maximum for Yosemite and the ice and in that area. And if you saw Ned Bear's talk yesterday, you saw the poster printed up on the wall, and we have it over there leaning against the wall because we haven't put any artwork up yet. So those are the talks for this morning. Really excited about that. And then after lunch, we'll have the ASO team updates, just what you can be expecting, and then what's going on in the background that you don't necessarily get to see, but that's working toward improving the products and efficiency and shortening latency, et cetera. And then we'll have the final panel discussion today, and this is largely an open discussion so that we can get into the topics that we didn't get to cover, or revisiting some of those that we did. So it's 9:10. We can be on time right now. Liz, is there anything I'm forgetting before I start the introduction of Steve?
I don't think so. Most people, I think, know the drill at this point. Feel free to drop your questions in the Q&A or in the chat, or you can raise your hand and we will unmute you.
All right, great. Thank you. So, so I'm really excited for us to get to hear a keynote from Steve Haugen, who is the water master for the Kings River Water Association. I first met Steve when Frank Gerke took me by the ear and walked me across the room at one of the cooperators meetings and said, "Tom, listen to what Steve has to tell you. Steve, tell him all about what you need." And I'll never forget that first discussion, and every conversation that we have. I come out of those conversations with a much fuller brain and a much better brain. Steve has been a huge advocate of this program as well as others to advance water management in California, and by extension to advance water management in the Western US and the similar places around the world. He has been the water master for the Kings River for the last 20 years. Despite looking so young, and so he's experienced intense drought. He's experienced the heavy years of the 90s and the 2000s, and has also been dealing with us coming into the really intensive periods of greater federal regulations on flows, a growing population, and now us running into the nonlinear part of climate change. So the experiences he brings are broad and deep, and so we're really fortunate to have Steve Haugen talk to us today. Steve, take it away.
Very good. I'm going to go ahead and do a share screen, and I do have a few slides here. And it's that one. Share. I'm assuming you can see my slides at this point. Okay. Quick disclaimer. Let's see, maybe not a disclaimer. Title of my presentation is A Reservoir Operator's Vision for ASO/ARS. California's calling it ARS, the Airborne ARSS. I think I got that.
Just say it, Steve. They're calling it ARS.
ARS. Airborne Remote Snow Sensing. I drew blank on what I put there already. I'm going to talk about it primarily from a Kings River perspective, but I'm also recognizing there are a number of other reservoir operators out there. I tried to capture some of the other issues, some of the other concerns and desires, but at the end, I think we'll have time for some question and answer, and I would encourage the other operators that are on the seminar today to chip in with their thoughts, their additions, and in the discussion later today. I'm not intending this to be an all-inclusive or an exclusive list. I'm trying to characterize the best I can. So with that, I've got a picture of Pine Flat here. These are the reservoirs that we need to manage. In this case, it's Pine Flat. For me, this holds 1 million acre feet. This happened to be in June 2006. We're at just shy of 970,000 acre feet. Peak of the flood releases, we had 11,000 CFS coming out of the reservoir. If we keep in mind, I'll go through some of our pictures. About 4,000 of that was going out as flood release. The remainder was being used locally. We're maximizing hydro generation at that time and still having to spill. And at this point, we're having a lot of impacts to a lot of folks downstream. So again, trying to characterize what we have to deal with on the ground basis and why we're engaged with ASO. Oops, what did I do here? Is my screen still showing?
You are not.
No.
Okay, what did I do here? Let me try that. There we
It's
go.
coming. It's
Okay.
coming.
Yep.
See if I'm going to advance through my slides here. It worked earlier on the test. Oh boy. Okay. Screen share. You want that one? I want to share that. Now, why is this not wanting to share for me?
Are you using the arrows?
The PDF thing?
This is a presentation. Okay, there we go.
There you go.
Okay. Sorry about that. So, starting off, we got some basic human needs that are out there. Air, water, food, shelter, and then goes off to, you know, a bit debatable list of criteria, but we need water to survive. It's a basic, essential human need. And we're being tasked on a daily basis for more intense management of our water supplies. We're getting more diverse needs. We're discovering how short we really are in the West. You know, there's a whole host of regulatory issues that are out there, a whole host of societal issues that really, it boils down to water. And for the folks that are on this call today, you know, that's the key item that we're really focused on here. So why is KRWA, Kings River Water Association, interested in ASO products? There's a whole host of items, and I put this bulleted list together. You know, I like to say our liabilities are outpacing our ability to forecast. What do I mean by that? We have forecast data coming in that's giving us information on how to operate reservoirs, how to allocate water. Well, with increasing populations, with reducing channel capacities, with aging infrastructure, we're being asked to do more with the same tools that we had 30, 40, 50 years ago. And to utilize those existing infrastructure and tools, we need better data. And our forecasting tools aren't keeping pace with the desires and needs of society. And so we need to, you know, anything I can do to help step up that level of forecast, to me, is a goal that we need to strive for. We've got management risks that I have to manage. We manage water allocations. Internally, we have to allocate water that comes out of Pine Flat to 28 different water right holders. Outside of that, we have a number of other, a relatively small group, but we have a number of other folks on the river that take water as riparian water users. So water allocations can be a bit of a challenge. We have flood management, drought management. Really, on the Kings, our hydrology is so variable. We're in one of those two states. There is no such thing as an average or a median year on the Kings. So we water management, water scarcity is out there. We hear about it every day. Infrastructure challenges, optimization. We haven't built a reservoir in California in, I think, 20 years. We haven't built an on-stream reservoir probably in 30 or 40 years. We are not going to be building any more storage. So how do we get additional yield out of our systems? We do it through forecasting and operation, optimization. Our infrastructure in the valley. For those of you not in California, we had a legislative proposal the past two years to add funding to our major conveyance structures, the Bryant Kern Canal, the California Aqueduct, the Delta Mendota Canal, to restore capacities to those facilities. In the meantime, we need to be able to forecast to best utilize those facilities to get the water to where it needs to be. Again, in California, we passed the Sustainable Groundwater Management Act. I believe that was 2014 or 2015. It mandates that we have water balance within our groundwater basins. That's about, the deadline for that is about 17 years out now. That's a blink of an eye in the amount in infrastructure in that. Some forecasts show that we're 1 million to 2 million acre feet of water shy within the San Joaquin Valley alone at achieving a balance. Possibly more than that. And that could result in 500,000 to 1 million acres of fallowed farmland. Again, major impacts to society, the economy in the valley is an ag-driven economy. So lots of challenges there. We got competing needs, and in some cases complementary. We got agriculture, urban needs, disadvantaged communities, environmental needs, all coming forward, and all of them at an elevated interest and need. We have water rights challenges. The shortages caused by sigma, shortages caused by water scarcity, climate change, it's creating water rights challenges to the water rights system that we've not seen before. How do you take 100 years of known, predictable water rights system and turn it on its head? Creating some real challenges for us. We have environmental management that we're starting to overlay of existing structures, existing operations. Again, new paradigms we're having to hit. We're hitting extremes in our statistics, our frequent diverging of trends. In the last 10 years, we've had the highest monthly inflow. We've had the highest average monthly temperature. We've had the highest monthly minimums in the winter time. We get these extraordinary years, drought and flood. Everything from a statistical standpoint seems to be hitting extremes lately. And more of a feeling than probably fact. A lot of it is fact, but those extremes are outpacing our historic statistical models. Along with those extremes, fire response. Look at the forest fires that we have. We've got the Dixie Fire this year that's, is it going to break 1 million acres? That's the size of the Kings River service area. It's a phenomenal scale of fire. And we're seeing those up and down the valley. And across the West, that's really challenging to us. Okay. So a bit about the Kings River service area. Here's our upper watershed. This area, it's about 1 million acres, lies in the Kings Canyon Sequoia National Park. We've got the South Fork, the Middle Fork come together. That covers about 80% of our unimpaired flow. No dams, no man. North Fork here has a couple of hydropower facilities on it with about 250,000 acre feet of combined storage. And those go into a terminal reservoir at Pine Flat. This is the crest of the Sierras. We have the San Joaquin watershed to the north of us, the KRWA watershed to the south, and the Kern tucked in right here. So the water out of this river comes down, hits Pine Flat. Pine Flat's gross pool is at about 1,000 foot elevation, outlets at about 500 foot elevation. So from there, we make our way onto the valley floor, providing water service to about 1 million acres and about 1 million people. From there, water can go south into a terminal lake. This area is fully farmed. But if we get into severe flood control situations, this area becomes a lake again from inflows of the Kings, the KRWA, the Tule, and the Kern down to the south here. So there's a lot of challenges for flood control. We have an outlet that allows us to put flood flows out the North Fork here, or turning into the San Joaquin River at the Mendota Pool. Typically, the Kings is the last system to flood release in the San Joaquin Valley, and the first one to go off. So by the time we have water going into the San Joaquin River, it's pretty well at capacity with other existing flood flows. So there's flooding challenges here, but just kind of some general lay of the land items there. Kind of looking at our upper reservoir, the upper watershed. The red stars is our sensor network. We got 8, again, it's about a 1 million acre watershed, 1,500 square miles for you to think of it in square miles. The red stars are our snow sensors. We have 8 snow sensors. We're lucky if we have all of those working in any one year. Again, aging infrastructure. Some of those were put in the 50s when Pine Flat were built. There's been various upgrades over the year, but again, aging infrastructure. The yellow dots are our snow courses. We have about 20 snow courses. Each of those snow courses are roughly 10 holes per course. Some of those up to 1/2 mile in length. So overall here, we get about 200 data points if you count every hole of every course and our snow sensors. Not a lot of data. ASO, awesome data set. We're talking something I think I figured is about 4 billion measurement points. Gets translated into roughly 1 million pixels over the watershed. Man, what a huge improvement. What a wealth of knowledge. We want to keep facilitating. We want to build on that and grow. And I'll talk a little bit more about that. This next slide, I'll point to the blue area. The blue area on this map is the portions of the watershed over about 6,500 foot elevation. Roughly our winter snow line, kind of historical average snow line. In wet years, or big years, we can have snow at 3,000 to 4,000 foot elevation. 2006, we went into April 1st with about 4 feet of snow at 4,000 foot elevation. We went through the month of April. Snow sensors, snow courses, nothing changed in the watershed during the month of April, yet we had 400,000 acre feet of runoff. Where did it come from? Matt made the presentation yesterday. Where did our snow go? So we have wet years. Where did this water come from? Dry years. Where did the snow go? Lots of questions, and working on the answers. The pink part of this map to the west over here is the parts of the watershed that are over our highest snow sensor. Fortunate for us, I've always said this is about 20% of our snow shed. After hearing what some of the folks in the Colorado basins have to deal with, I feel pretty fortunate right now. But that's a real unknown that has a big impact for us for runoff. This I'm showing the various wilderness management zones, but think of everything east of this black line, everything to the right of the map is wilderness. No roads, no access, no machine access. It's very difficult to monitor this watershed. We're reliant on, if we're wanting to expand our knowledge of this watershed, it really goes into the remote sensing aspects. And that's where ASO is a huge value to us. Other basins in California, some of them have a significant amount of wilderness area as well. Some of them not so much, but for us, the wilderness aspect is a large constraint. We also mentioned military operations area, this blue line across the map. Everything south of that is in a military operations area. North of that, we have fairly unrestricted data gathering. This brings its own challenges forth and areas we need to work on and try to improve some of the regulatory. So again, I threw this picture in. This is looking up the South Fork as we're flying over Cedar Grove, headed up to our Bench Lake sensor. kind of gives you a concept of what some of the watershed looks like. We're probably, the bottom of this canyon's probably in the 7,000 foot elevation, and the top of the peaks in this picture are probably in the 10,000 foot elevation range. This was taken March 27th of 2008, roughly April 1st, considered the peak of the snowpack. That was a 72% water year. So you can look at this canyon under heavy years, can be white. The entire picture is white. In drier years, you'll see the lightest of dusting. So it's a very diverse watershed, not dissimilar to many other watersheds in the ASO program, but definitely something to keep in mind when we're trying to go into operations. I put this in here yesterday. There was a mention of a double peak of inflow. This is the inflow we experienced 75 days between roughly the 1st of May and about the 10th of July, the inflows to Pine Flat, roughly similar to natural flow for the system. We had, I don't know, 1, 2, 3, 4, 5 peaks maybe. Real challenges at operation, a real yo-yo. And when you overlay the operations manual, Pine Flat Reservoir is an Army Corps of Engineers facility built for flood control. We're allowed to store water in it at certain levels as long as flood control is covered. So, you know, the variability that's coming is a real challenge. So 2017 was our 3rd wettest year on record, 4.1 million acre feet. 2 years prior to this, we had our driest year on record, 360,000 acre feet. That's a 10-fold, probably 11 or 12-fold difference between wet years and dry years. Highly variable water supply. And some of those initial reasons I listed as why is KRWA interested, we need to be able to capture this water and put it into storage. We have 1.2 million acre feet of storage in the system. Operationally, there's probably somewhere in the 500,000 to 600,000 acre feet of storage, surface storage that we can use. We need to be able to put this water into groundwater storage, recharge our aquifers. Our aquifer is probably a million acre feet, probably 100 million acre feet in size. We have several, probably 10 million acre feet worth of storage in that reservoir that's operational storage. It is our long-term storage. We need forecasting tools that allow us to operate early enough and spread these peaks out so that we can optimize our surface storage and get this water into groundwater. For groundwater recharge, I can't handle 17,000, you know, here one day we've got 9,000 CFS, here we got 17,000, and up here we got around 28,000 CFS. You know, we can't handle that kind of variability. We have to have consistent, steady flows for groundwater recharge to be really effective. And that is what's being looked at as the solution to our long-term water supplies and our groundwater overdraft, at least in the Kings River service area. So our high variability, seasonal variability from year to year really is driving some of our thoughts. So what, as a reservoir operator, what's my challenges? And we've got technical challenges. What do I mean by technical challenges? Model uncertainties. You know, just our data collection, uncertainties in the, you know, the resolution of our instrumentation, you know, in the modeling techniques and that. I've got uncertainties in the weather. We're always looking at what's the future weather. In dry years, we're always asking, well, what's going to happen if there's no more rain? In wet years, it's like, oh my gosh, how much more rain can we possibly get? So we're always looking at those uncertainties and trying to quantify those, and you have to manage to those uncertainties. We have downstream water demand. we spent the last couple of days talking about uncertainties in the forecast data. I have similar uncertainties in the water demands. We know our crops have certain demands, but the practices of how people deal with it and manage it, there's a lot of uncertainty there. There's a lot of demand theory we can come up with out of the utility companies, like sizing phone lines, sizing power lines. How big do you need? Those help us, but there's still a level of uncertainty just with our own downstream water demands. We have uncertainty in policies. Sigma, changing water, Sigma, in-stream flow initiatives, a number of items in California regulatory environment that's changed how we need to think about stuff. Some of that is policy driven through elections. Some of it's through regulatory. I mentioned political here. I don't have a year that goes by that I don't have some elected official calling me, asking me why. Why is it dry? Why are we not delivering? Why do you have water in this person's living room? It comes from all levels. I have it from senators in the federal government down to the local elected officials and city council members, and then public perception. Managing that public perception is really important. They're influencing your electeds. They're influencing your boards that are managing what's going on. So, those are challenges that I have to deal with that aren't necessarily tied to the forecasting, but the forecasting data drives those communications. And so how we are able to present, and I've got some additional slides on communication here later, but I can't emphasize enough, we need to be transparent in our data collection and in our results, and the ability to interpret that for the public. I'm gonna steal a few slides from the last several days' presentations. Tom ran this through the evolution of ASO. So this early part really was the development of the program. This mid part, we brought it into an operational tool. And I'll say this later, this last couple of years, we're rolling cars off the assembly line. We got an assembly line going. I'm not saying we're a Model T, we're a Model A. We're the second generation. We're doing awesome here. Well, we want to get to an e-truck. We want a V8. We want an automatic transmission. We want self-driving. We want power steering, power door locks, air conditioning, all of that. And that's our next step where I see this going, is we've got a great tool. Now we need to exercise it. And so what do I see as the program needs? I'm going to go back to Tom's slide. Here on the right side, Tom's got a whole bunch of cooperators there. There's more outside. They're utilizing the data and bringing this together. We need to think about that. Dave Rosardo does a great job with California Cooperative Snow Survey Program. For the field measurements, collaboration that brings that together, that's an amazing program. That's been a success since I think the 30s. I might have that wrong, Dave, but we're going into 80, 90 years worth of collaboration in that program. Excellent program. I see our technical needs as we're moving forward. We need to maintain that, expand it, and build upon those programs. We need a cooperative program, a collaborative program. And that coordination needs to include local operators. They've got some of the best knowledge about what's going on within the local watersheds, within the systems. We need state and federal agencies. We need the funders. Who's paying for flights? We need the collaborators. And when I mean collaborators, the folks that are developing models, the researchers, the host of folks that are here on the ASO conference over the last several days. We have the researchers, we have the end users. That we need all of those folks together. And for a program to be successful, we need the folks doing the data collection and the processing in the loop as well. Depending on how that's being done, where that's being done, whether it's a private entity, there can be some challenges with contracting and that, but they need to be part of the discussion, part of the loop, so we know their capabilities and their limitations. Everyone involved needs to be invested in the program. To me, these are all key to a wildly successful program. If we don't have this, we're going to have problems with sustainability in our programs. One of the, and so from my perspective, what does an operator need? And I've got a couple additional slides of some more distinct needs, but generally, ASO technology is proven and available. We know we got this great tool. We need consistent funding. We need to know that this is going, that the data, the process, the models are going to be available into the future. If I know that, I can start investing local funds into better refining and how to utilize this data. Right now, I've been able to use the data to provide confidence of where we're at. I think there's another step or two at a minimum where I can further integrate this data and go to much more, make the data much more useful to us locally, but I need to know it's going to be there to make that investment. Public data sets have the greatest value. What do I mean by that? I can pay ASO Inc. to collect data, I being Kings River Water Association, or the state of California can pay ASO to collect the data and house the data. We may both get the exact same answer. I shouldn't say may, we will both get the exact same answer out of that investment. But perception, when we go to run the reservoir to operate, that data coming through a public agency has so much more value, credibility, and it's credibility that it comes with. It doesn't have the perceived biases that I may be bringing to the table. So having these public data sets has great value to the program. And I kind of mentioned this next one, perceived unbiased sets have great value. I mixed the public data set and the perceived unbiased sets. We have to have that unbiased set. And then the last item that I really need is we need to move from snowpack properties to getting that snowpack in the reservoir. That modeling, I need to know what's in the reservoir. Having the snowpack properties is key to getting there, one of the key data sets, but I really need to know what's going to make it into the reservoir. As I mentioned, 2006, we were getting water in that wasn't coming from the obvious snowpack. ASO would cover that. Likewise, this past year, where'd the snow go? Key, we really need to work through that. So I stole this from Dave Gotchis yesterday. Awesome presentation, Dave. Home run with that. And I don't really need to spend any time with this, but can I'm going to take this as a menu and I say, I want it all. Can we have it next year? We need this now. So folks that are working on this and incorporating these ideas into the models, stay at it. The folks that are able to fund these things, we got to keep the funds going towards it to improve the development, to make these things, to bring these tools in. And it looks like we can do it with the data that we have available in some regards. So, so from that slide, additional needs. We need public operational physical models. We need models that are responsive to the changes we're seeing in the watershed, in climate, in runoff patterns. Again, I talked about the anomalies earlier. We need those. We need to refine the time steps. We've traditionally been able to manage with seasonal volumes. The demands that are being placed on us as water managers require much finer data much finer forecast, ideally daily and very far out. We need to implement and integrate the prior slide as soon as we can. We need to continue research and refine our data collection and modeling expertise. We need to continue that investment. One of the challenges we have with elected officials, they want the silver bullet. They want to think of this, oh, we got this tool, we're done. And no, we need to keep advancing the science. We need to keep advancing the research. And we got to pound that message home that, yes, this is a great tool. It's a good advancement, but it's part of the evolution. And then probably our biggest one, we have to reduce. I would like to say eliminate uncertainties. I know that's unrealistic, but I'm going to set a lofty goal. I'm going to say eliminate uncertainties, but reduce and define. Where are they? What are they? We see our classic funnel diagrams. Some of that's based on weather, some of that's based on model uncertainties, some of that may be based on data uncertainties. Knowing where those are at and how each model or each statistical tool, where those are embedded in what magnitude is really important to a water manager. When I see a funnel diagram, I'm going to go back to one of the prior flood years. We were at June 1st, roughly. The difference between the high forecast of the CNRFC and the low forecast of DWR was 500,000 or 600,000 acre feet. We were managing Pine Flat to get to within 1,000 acre feet of full. That level of uncertainty within 30 days, I can't manage to. I need to know where the uncertainties are at so we can manage risk of whether we need to put more flood releases out and possibly damage downstream users. We may damage downstream residents, downstream property owners, but the damage is much less than if we err with too much water at the end. So, again, we need to have those uncertainties defined and reduced to the greatest extent possible. Again, borrowing Tom's slides, great process of laying out what the different steps in the processes are. I'm hopeful that we can really move forward with enhancing and adding to each of these steps, each of these phases. Let's squeeze more out of our flights. If there's other sensors that can give us other properties, if we can get to the point where we're getting soil moisture with it, ice layers, knowing more about the snowpack, what's the water content in our meadows, the surface storage within the watershed. If we can start getting that, the processing, we heard a whole bunch of presentations over the last several days of lots of cool things we can get out of these data sets. We need to keep working on that and bring it in. The modeling. I will take every and any model I can get. Currently, I'm able to look at there's forecast data and then there's models. There's about 3 different models that we end up getting information out of. Some of them we're able to access through the private utilities that they're willing to share some of their information that is not generally public. Those are really helpful. And then visualization and getting the data out to the public, out to the users, key. So one of the things I look at with the models out of this prior slide is model reliability. We got to be able to handle data blackouts due to weather, regulators. You got FAA that can come in and inspect a plane and shut a plane down. We got military operations areas. If we're doing ground maintenance, have Park Service, Forest Service, other entities. We got equipment challenges. You can have equipment challenges with a spectrometer, with a plane, with a wind sensor, a GOES antenna, all kinds of issues, unexpected issues. Our ground truthing for the last couple of years. Who would have ever expected a pandemic to come in and limit the ability of folks to go out and collect ground data? Personnel changes, people retire, people change jobs. We have to be able to have reliability of our modeling systems under those scenarios. The next piece that I look at that I'd love to see out of our models is the ability to provide synthetic data streams to go back into some of our other methods. Again, kind of paralleling off of we missed a number of snow course measurements because agencies couldn't fly, couldn't go out in pairs to collect the data. We had our traditional modeling techniques, our traditional forecasting tools. Having that synthetic data put out is a way to backfill, maybe not the preference, but it's a way to backfill those data streams and make some of those other models work for us. Some of the things I'd like to see. We need to be able to communicate results. And I've listed a bunch of stuff here. Expressing the uncertainties, I covered that area. Avoiding misapplication of results. I get so many calls during the year where somebody got a snippet out of a news article or off of a web page, and they're saying the reservoir is going to flood, and they're looking at the wrong data set. They're looking at the wrong stream, or they've converted the units to some strange unit. And we need to be able to communicate results such that they're not misapplied. And then audiences. We have high informed users, power users. I'm going to say those are the reservoir operators and our forecasters. There are probably some others that fit in there, but those folks really understand the data. They got a pretty good feeling of what's going on in the background. They may not know how to do the data regressions that ASO Inc is doing, but we got a pretty good feeling what the data is and what's there. You got non-traditional users. You got emergency response folks, OES, sheriff, police, fire, city parks departments, using this data to determine whether they open things for recreation and other stuff. You got regulators that are using the data to change water rights or administrate water rights on the fly. We need to know inflection points, when transitions are occurring. We got biologists using this data. Various regulators, water quality, water rights management, locally Fish and Wildlife uses the data to determine when to stock fish, when not to stock fish, when to enforce certain fishing regulations. They're managing their staffing. They're managing water quality from, looking at salmon migration and those kinds of things. We got elected officials looking at the data. These are folks that might only have 2 minutes a day to look at the data with no technical expertise, but they're wanting a snapshot of where we're at in the state, in the county, in their city, in their districts. You got the general public looking at this. That can be farmers, citizens, recreationists or fishermen, rafters, hikers, bird watchers, all kinds of folks out there, business owners that are reliant upon the river, marina operators, rafting companies, those types. And then reporters. I've got reporters always asking where to get data, and they just grab it and publish it. Well, they need to know what they're publishing. So communication of results is key. And I'm almost through here, Tom. I think I think this is my second to last slide. So what's a reservoir operator's utopia? If I can get my list here, at least the operations part of my job becomes very, very simple. And I'm probably out of a job from an operations perspective, but where do I want to see as a goal? This is my lofty goal out there. Public operational physical based models, models that are responsive to our changing conditions. I still want to maintain our statistical models. They're still useful. We have many folks that understand those, but our next step is really getting those public operational physical models out there. I need a forecast that goes out a year. And I need that in a daily time increment. We came in March. We knew it was going to be a dry year. First question we had in our office is, okay, what's that going to be doing for temperature management in October and November? How are we going to end this year? And so knowing where the inflection points are for where maybe a water right changes, or when additional releases are needed for fishery purposes, or how does that translate into temperature management in the reservoir? You know, that's where we need those long-term, high-resolution forecasts. We need to eliminate or define as much uncertainty as possible. No blackouts in data or model results. We need to get reliability in our data monitoring systems, and the model results. We need to keep those coming. We need simple to communicate results. Again, that's that public piece. No perceived bias. We need to try to keep the bias out of this. And that's where that collaboration between all various parties come into play. And we need these results 365 days a year, 24 hours a day. In 2017, we were on a call with DWR, the Corps of Engineers, and the forecasters twice a day for about a 2-week period during the height of our flood release. You know, what are we expecting the change to happen today? Very short term versus some of the long-term forecasting I was just talking about earlier today. And, you know, storms never seem to happen Monday during bankers hours, Monday through Friday. Storms always come in on a Sunday night at 2 a.m. Or, you know, the decision is Saturday morning, you wake up, there was a levee break. What do we need to do? And you're rerunning all your forecast models on while your kid's playing soccer on a Saturday morning. So my utopia has these items in it. In closing, you know, water, it's essential to us. We have to get our modeling down. It's essential to our physical survival, food production, our communities, and our local economies. And we got to just keep pressing forward on advancing with data collection, model accuracies, and reduce and eliminate the uncertainties. And with that, I'll close it, and Tom, you take it from there. I'm open to questions or input from the.
Steve, thanks so much for that. That really tour de force. Yeah, I think I'm gonna have to spend the rest of the week thinking about that and the implications and where we're gonna go internally, as well as in the communications with DWR and the individual users. Let's see, do we have a question out here from
let me
Gus?
stop share. I'm going to stop share on this.
Can we free Gus up to ask in person and interact?
Sure.
Take it away, Gus.
Hey, Steve, thanks for the presentation. It's really interesting. I am constantly thinking about this problem, and several times in your presentation, you mentioned that sometimes the uncertainty of the forecast is not really actionable from a management perspective. And whenever I hear that, I know a lot of times everything gets pushed into forecasting, like we need better, we need this. I'm just wondering your perspective on, the management criteria. Sometimes it feels like the expectations for management just plain exceed our ability, to deal with the uncertainty. And I'm wondering if you could just say a few words about that aspect, or maybe that's just inevitable.
Well, and I think that was in my opening statement of the, basically our liabilities are outpacing our ability to forecast. Trying to optimize and squeeze every last drop out of a system is forcing us to try to, assure that reservoirs are at peak storage during the season. And assuring that we're putting as much, minimizing channel capacities when it comes to flood control. So we're having, as an operator, I have to take, that forecast data and, the River Forecast Center and DWR, those are both credible forecasts. And so we have to take that data and make the best management decision we can with it. And in the case of that particular example that I was relaying to, we only had probably at that date and time, probably about 30 to 50,000 acre feet of flexibility within our system. So I've got 500,000 acre foot of range in the forecast, and I probably realistically have about 50,000 acre foot of flexibility. We have to start making management decisions based on our knowledge of those forecasts and of those tools. And in that case, that was direct access to the forecasters. I'm talking to the Weather Service. Where do you see your errors? Where do you see, what's your limitations? What do you think you're high? Do you think you're low? Same thing with DWR, on the phone with those forecasters saying, did you have to backfill some data? What's your concern? What's your gut feeling? Do you think you're high? Do you think you're low? Are you on do you think we're leaning towards the 90% or are we leaning towards the 10%? There's a lot of personal communication that ends up there. And that's the nuance and the art that goes behind operations. And to the extent we can knock it out of, eliminate that in the forecast, eliminate the uncertainty or understand the uncertainty in the forecast, that helps us with the art of the operation. Hopefully I got that. That makes sense to you, Angus.
Yeah, thank you, sir.
Let's see, we have Bebek, your hand is raised. Did you have a question, or I noticed that it's been raised for a while. Ah, you caught it. All right. And then Dave Rosardo's talking is permitted. Dave, do you have a comment? There you are.
Well, I think, what you heard from Steve and you kind of heard from me yesterday too, I think lines up quite well. And probably not surprising because we talk a lot, but I think Steve said it well. And, there's so many aspects of this, right? And I think the question that Gus brought up was good. Well, a lot of this gets pushed to forecasting, but what are the other challenges? Where does some of this come from? Mike Anderson said it yesterday too. The decision makers above us, they like shiny objects and nice pictures, and to Steve's point earlier, well, sometimes they want this silver bullet. So this is unfortunately what clouds all of this moving forward a little bit. If it was up to everybody on this call right now, we would all agree to move forward as fast as we can and pay for it as quickly as we could. But it's certainly not that easy. But yeah, I obviously, even just this week, I'm getting so many emails off to the side or this or that. Hey, do you think it helps with Floodmar? Hey, do you think it helps with this? Hey, and it's pretty easy to answer those emails. Yes, and yes, and yes. Just the email I got about Floodmar yesterday, just even the difficulty of writing back and admitting that, well, from a DWR perspective, those of us on the hydrology and the runoff forecasting side haven't had quite yet a chance to talk to the people in charge of the Floodmar projects. And that's just a recognition of how busy everybody is on a regular, day and month, and then you add in something like a drought emergency, which, exponentially increases how busy we are. So I guess that's, just rounding out Steve's comment is, we're all facing these challenges, and then it's a matter of finding the time to deal with them and fit them into the grand scheme of things, and then convince the people with the purse strings.
Well, and to that extent, a program like FloodMAR is a flood managed aquifer recharge. It's a rebranding of groundwater recharge. No offense to the DWR folks, but the improved forecast, the confidence that ASO gave us in 2017. We put about 75,000 to 100,000 acre feet of water in the ground leading up to a flood release that we otherwise would not have done. The program's already showing results. To the extent we further implement it, we gain the reliability. I think we can exercise that immensely more. Again, stretching our flood releases, utilizing our existing infrastructure directly impacts FloodMAR. It's the optimization of the system for all of those needs: FloodMAR, environment, water demands. So real quick there.
All right, Steve, thanks again. I know you have meetings this afternoon, but it sounds like you might be able to join us partway through the discussion period. So hoping that we'll have more time with you then, and
I'll try to be back on about 2:30 or so. So I'll let you know.
All right. Thank you. So why don't let's take a break and come back at 10:15, and we'll get going. Kat will be chairing that session, and we'll be into the next talks. Thanks again, Steve, and thanks everybody for being on here.
Okay. I wear this hat to sleep, Jeff. I never take it off. It's my ASO hat. Gotta wear it. Okay. Thanks everybody for coming back. We're gonna kick off the next session this morning. The first talk, we have a combined talk with Jacob Wasilkowski. He's at ESRI and he's one of the programmers we've been working with. And we have Evan Burgess, our lead data scientist, and they're going to talk about some really exciting web development stuff that we've been doing in combination with each other and also for data delivery. So this is hot off the press here. I'm excited. Okay, take it away.
All righty, 1 second. All right, how's that?
That's your desktop.
We see that your Slack and your desktop.
Oh, hold on.
Or your personals, Evan.
All my personals. Let's try that again. It said number 2. Number 2. Oh no, don't leave meeting. Hold on.
Good thing we don't do any technical
I was supposed to be like the technical guy. Yeah. Is that better?
That is much better.
Okay. All right, yeah. Way to have lead data science can't show his screen. Okay, yeah. So it's kind of a change of pace, but the end of Steve's talk actually ended up being a great segue into a bunch of the stuff that we're going to talk about. I was happy to see that some of the stuff that Steve, that you were talking about in your dream water management list of stuff that we're working on. So hopefully everyone will be psyched about this. So I'm going to be giving this presentation with Jacob Wasilkowski from ESRI. And for the most part, everything that I'm showing you is actually work being done at ESRI. There's a pretty extensive team. I'm listing the majority of the people that I'm familiar with working with this, but I think there's actually more people in behind the scenes too. But there's a lot of very specialized expertise that we've had the opportunity to work with at ESRI, and as a result, we're getting some really cool. We're getting a really cool application out of it. So let's move forward. There we go. So I think ASO. I think we're understanding. How do I say this? I think in the past, ASO has mostly been focused on data delivery. We, at the past, when we produce data sets, we are distributing zip files with raster data sets and then aggregated information and plots and things in PDFs and so forth. But the direction that we really want to go is in providing a fully fledged decision support system for water managers. And that is software that is custom designed to help water managers make decisions and do so without having to download data and do a bunch of tedious plot making and other things that they need to do to not only make decisions, but convince others of those decisions. So we're trying to really ease that process. And again, ESRI is a strategic partner of ours, and not only do they have all of the mapping technology that everyone is familiar with, they also have some really crack web developers, that Jacob being one of them, and they're working with us to build a really cool piece of technology. So I think, do I have this? Oh no. Yeah, so as it's turning out, I think one of the coolest things about this application that we're going to show you guys is that kind of the wish list of the decision support system that we've decided on is sufficiently complicated that there's no one piece of technology that can do it. Out of the box, ESRI software can't do everything we want. We as ASO certainly don't have the expertise to build this. So the end product is kind of going to be this really cool melting pot of ESRI technology, a lot of custom code written by Jacob, a lot of custom stuff and open source stuff developed by us. And so it's really kind of cool to see all those things come together. On our side of things, we've had to build a whole bunch of new database structures and APIs that will kind of support all the stuff that Jacob's going to show you. We're also very lucky to be able to utilize ESRI's authentication system. So this will allow everyone to get a login, and it allows us to control access to data. There's been a lot of talk about public data, and certainly in the case of California and Colorado, that's largely the case, but there will be cases where data is not necessarily public, and we need to make sure we're ready for those situations. And the authentication system also allows us to customize things for users. So when you go on the website, you can come on and look at your basins of interest specifically. So rather than talk more, I think the way this is gonna work, I'm gonna break now, and I'm gonna let Jacob give you a demo, a live demo of what has been built so far, and then he will stop, and then I'll kind of finish with some wireframes of where we ultimately want this to end up at the start of the season next year. So I will stop sharing. And Jacob,
Okay.
you are ready to take it away.
Yeah, thanks. Thanks for the intro, Evan. And I'll share my screen here. I'll be sharing, let's see here, I think I'm just going to share the browser just to focus on that, and I'll get that going here. Excuse me. Okay, and looks like it should be up now. Yeah, Evan, so thanks again for the introduction and also the kind words. It's been, before I really jump into the demo, I just want to take a moment to thank you all for inviting me to be here today. And genuinely, it's been a pleasure working with you all on this project. I personally, before I turned into my day job, turned into being a web developer, I have in the long distant past an academic background in pixels and remote sensing time series analysis. So this has been such a joy and so much fun to collaborate with you all on this and to really stare at, get a taste of the data that you all create and fly and analyze. And it's been a lot of fun to help kind of bring it up into the web and give people access to what you do. So again, thank you for having me today, and thanks for the overall collaboration we've been doing over the last year. So what you see now is the beginning of the demo, and this is as we've been calling it internally, the landing page. So we have your ASO's kind of, we're going for like this branding, marketing look and feel here. A landing page just to explain like what's this all about. This is going to be kind of the front of the portal to start accessing data sets. And we have some blurbs on the left, touching on those high points of what ASO does and can do for you. And then on the right, we actually have, it's a map, it's an interactive map, but it's also the primary way to start gaining access to some of this data. So I can jump over to this spatial mapping bookmark, if you will, to find out what basins are being flown in Colorado. And again, this is kind of demonstrative data at the moment. Flying back to California, I'm now encouraged to log in or sign up. So I'll show the sign up form just to give you a preview of that. And Evan, if you want to jump in and kind of explain what this might do one day, feel free to.
Oh, you're catching me off guard on what to say. I mean, the idea is that we'll give all users access. We will have specific, basically anyone who is able to, in order to download data, we want you to sign up, but you don't need to be essentially a paying customer of ASO to log in. And just once you log in, depending on whether you are a paying customer or the public, it will affect what services you might get access to. But everyone will be able to download data just by giving themselves a login, and that's free, and you'll be able to access the data.
Awesome. Thank you for jumping in there. I appreciate that. Right. So at this point, what I've done as Evan was mentioning, that I actually logged in, instead of going through the whole sign up process, I actually have logged in with credentials I already have. And no matter what, right here, I can start accessing these basins and learning about data sets that I can download. So first, let's take a quick look at Kings Canyon. If I click download data, we see a panel, a data download panel open up, and that's analogous to the previous zip data downloading pages, I think that your users are familiar with in previous seasons there. So it's organized by years and by flight acquisition times there. Start downloading those zip files. I think quite a few of you all are familiar with. Now, my particular user, Jacob Wasilkowski, has additional access, which Evan was getting to, for a couple, certain basins that I'm particularly interested in. So not just to download the data zips, but rather access this other piece that is in active development right now, especially this. And this is what we're calling more of a data dashboard, if you will. Very interactive map. We now see what we call in the ESRI world an image server, hosting data here and actually hosting pixel raster data. And we've just very quickly, for today's demonstration, put in just a sample of a few time slices here. And you can flow through those by dragging the slider, just to give you an idea of what was happening at that time in this basin. Furthermore, this is really exciting. We're combining and marrying this interactive map with interactive charts too. So now we have a hypsometry plot, we have this radio plot showing you, aspect, which way you're facing, or rather which way the slopes are facing, and increasing with elevation bands and information about your snow water equivalent there. So let's say I'm interested in north-facing slopes. Oops, I don't want to zoom that. I'd rather actually lasso select. I'm going to focus on some north-facing slopes. Just kind of highlight those in this interactive chart, and then again start stepping through time. And it's one of many ways that will come online soon that you can start really diving into the data of what the pixels on the map are trying to tell you and what's being rendered in the charts as well. And my particular user account has also access to, for deeper analytics for another basin, so I can switch right over to that. Different timeline, different part of the world here, and again, interactive plots that are combined with what we see on the map as well. Yeah, I think that's really the highlights there of what we're excited to show you. I'm happy to pass it back over to you, Evan, or I can leave something open if there's something you want to touch on.
Let's swap back.
Okay.
Back to the slideshow. Get it right. Okay. Okay. So that was great. The demo worked. Psyched. Well done. So the whole ESRI team, they are working hard, and so we this is going to continue to the spring season. And so what I have to show you now are some wireframes. These are put together by Michael Geig at ESRI, who is who his particular area of expertise is in user experience and user interfaces. And so this is kind of our template of where we want to go with what Jacob was just building. And this picture here should look pretty familiar from what Jacob was just showing you. The big difference and the added feature here is this timeline. Jacob showed you kind of a rudimentary timeline, but what we want to do is give you a very flexible timeline that actually shows a real timeline, not just each acquisition. We want to give you the ability not just to look at the current season, but to go back in previous seasons and click on acquisitions from previous years. And ultimately, what we want you to be able to do is to not just click on a specific acquisition, but to click on any date. And if you click on a date that is in between two acquisitions, what you will get is the snowbow model results for that basin at that specific date, updated with the last flight. So the idea there is that if it's been a few weeks, several weeks since the last ASO acquisition, and you're chomping at the bit to know what's going on in the basin, you don't just have to wait blindly to know what has changed since the last acquisition. You can come in here and see what iSnowball says is going on today based on the last ASO acquisition and modeled up until then. And then we have a new flight, then the whole thing updates to that flight and continues on. We have an animate button here, which would export a movie of your basin over the course of the water year. These plots should look familiar from what Jacob just showed. We're also working on a time series plot that shows you the 1,000 acre-feet evolution of the basin over the season and shows each lidar acquisition, but also the model evolution over the course of the season as well. The layers button, I think Jacob never clicked on it. It's fairly rudimentary what we have now, but eventually what we want to do is give you the ability to not just look at SWE, but depth, also albedo, and to be able to change and not just look at the data values, but look at the uncertainties. And ultimately what we want to do is also, when it comes to iSnowball, let you play around with various model parameterizations like temperature, shortwave dust reinforcing. So say, for example, you think that all of a sudden the snow is going to go super dark from a dust event. You could tweak the model a little bit and add some more dust reinforcing and see how that affects the model output in these plots. And let's see what else I want to say. So the other big thing, so Jacob showed that all these plots are going to be interactive, and they're also very similar to to what you're used to seeing in PDF reports now. But we also want to make sure that all of these plots are easily, you can download them easily, so you can plop them in PowerPoints without having to do a tacky screenshot or something like that, because we really want you guys to be able to take all these nice graphics and quickly put them into PowerPoint so you can go off and convince the people that you need to convince of these data and information. I think that's all I wanted to say there. Another feature that we're working on is giving the ability to compare two different times, or ask the question, how is right now compared to last month, or how does today compare with the same day 3 years ago? And so the idea here is that you can use the timeline and click on two different times, and then you're getting a map, and all of these plots will now show a comparison between those two dates. So you can kind of ask that question easily and get some very good graphics, so you can think about today in context of previous condition. And I'll say my guess is that this comparison feature and these model features, this is probably not a 2022 thing. I think this might be a little far off, a little optimistic, but we're working towards this, and it will happen eventually. And lastly, this is just a wireframe of an export modal that'll pop up. But in general, I just want to say we're really focused on making sure that this isn't just a cool website, that it gives you the ability to produce maps, plots, all the things, all the graphics that you need to convince other people of decisions. And we're still working on all the ways that we can make that easy and make those outputs look good. So I think that's all we have. I don't know how we are on time.
Okay, that was fantastic. I've got Tom here. He wants to make a couple comments, and we have some Q&A in the questions there. So I'll let Tom have a chat.
Let's see. Oh, I'm looking at
there we go. So so first of all, I couldn't stop laughing at the William Mulholland in the upper right corner. I'm not sure how many DWP folks we have on here, but if you don't know the name, go look him up, and you'll see the interesting twists. And then also go see the movie Chinatown, and the character that they turned him into there. So thanks Evan and Jacob for doing that, and I haven't seen the latest and greatest here, but I'm getting really excited about it. And I was also excited to see the questions that were coming in, and I want to let you guys refer to those. But the other aspect of this that is coming is an ability ultimately to have this be a module that is connected with your ArcGIS, and so then you'll have the full utility of ArcGIS and the ASO analysis and visualization tools, so this is really you're seeing the progress toward the mature phase of what we're building with ESRI, and as Evan put it again, that we're able to work with this team is fantastic for us. And I know that so many of our water management partners are users of ArcGIS and other products, and so we want to make sure that what we're building can weave in intimately with what you're using already, and then and see then advancement coming along. So
on top of that, the one thing I forgot to say that's very important is This is all still in development, and if anyone has, I'm already noticing some suggestions, such as Brent Duncan's comment. If anyone here has comments of ways that we could improve the stuff that we've shown, we genuinely would like to hear it, and we'll listen to your suggestions. So if you want to contact me, I'll put my email here in the chat, and let me know if anyone has ideas now or in 2 months or in a year or whatever. The questions I'm seeing, Andrew Schwartz asks, are 2 dates the maximum comparison, or will we be able to compare larger numbers of dates as well? I have not given that much thought. One of the limitation, if I show you the plots, if I go back to share my screen here, part of it has to do with just sort of how to visualize comparing more than 2 at a time. If we go back to here, this hypsometry plot here, it's easy to compare a whole bunch of times, and this plot works comparing more than 1, but this radial plot does not, and getting a map to show you subtract more than 2 won't work. So we could think about how we could allow you to compare more than 1. I guess if that would be of interest, I'd be interested in chat more with you, and we could talk about how to make that work. And Brent Duncan, we have not talked about GeoPDFs, but I will take that as a note, and we'll discuss that, see if that's a possibility. Did I get all the questions, or am I missing some?
Yeah, I think from the majority of the questions, some of them are more suggestions, and so I want to let everyone know that we are capturing every single one of those. The product is in development. We still have a lot of flexibility and aim as to what's going to end up in this tool, and so your suggestions here are really useful for us and important, and so we're grabbing all of those. Ned wanted to hear a little more about the design process, but in the interest of time, I'm going to cruise forward. But Ned, you can feel free to reach out to us on that and talk.
And also in the background here in chat.
And also in the background on chat, I've got Tom answering questions. So let's keep cruising. Next up, we have Arielle Koshkin. She's a graduate student at the University of Reno with Ann Nolan. She's working on the impacts of fire and hydrology in the creek fire in the San Joaquin. And Evan, I'm going to ask you to stop sharing your screen so Arielle
can hear her. That's
fine. And yeah, so Arielle went out and took a whole bunch of measurements this year, coincident with our flights, and she fed those back to us. We were able to use those in our operations. They were really valuable. And so I'm excited to hear about her research.
Thanks, Kat, for the introduction. Yeah, so we are trying to quantify these hydrological impacts when a large wildfire moves through a snow-dominated watershed. And we did this, as Kat said, in the creek fire, which is in the upper San Joaquin watershed. And so just some quick background. We all know that wildfires are increasing across the West. A lot of us are feeling the impacts of this this summer with smoke across the Western United States. And that these are potentially going to become more frequent with drier years ahead. And the intensity and severity of these fires is going to be highly variable, but definitely has the potential to increase and have massive fires on the scale of the Creek Fire, the Dixie Fire, the Caldor Fire. These are all huge fires burning higher and higher up in snow alpine watersheds. And so here's just a quick graphic showing that we definitely have more acres being burned over the course of time. This is specifically the US Forest Service, but I think the trend definitely holds true across the Western United States. And these wildfires have impact after they come through and burn. The snowpack definitely is changing. And we know this generally from Gleason and Nolan 2016, that the charred woody debris and black carbon that's shedded from these burned trees is being deposited on the snow surface. And this is decreasing the albedo and causing snow to melt out faster during the ablation season, and this definitely has major impacts downstream for water resources in these high burned areas. And so visually, I just want to give everyone a sense of like what I'm talking about here. So when you have a healthy forest with a tree canopy, the amount of light that's reaching the snowpack is actually going to be decreased. A lot of that gets lost in the canopy. And meanwhile, when it snows, that canopy is also going to intercept a fair amount of the snow. So we potentially will see a decreased amount of snow in the forest. And meanwhile, if that snow on the ground is not totally covered in forest litter, it's going to have a pretty high snow albedo. It's going to be pretty reflective and reflect a lot of the light that's coming in. When you burn down that forest, the forest structure changes and the impacts on snow are very different. All of a sudden, we have a lot more light coming in with no interception from the canopy. That canopy is also not going to intercept the snow that's going to fall. And meanwhile, that snow is going to be contaminated with the black carbon and woody debris that is shedded from the burned trees. So that is ultimately going to probably decrease the albedo and increase the amount of energy that's coming into that snowpack. So not only is it going to be less reflective, but it's also going to be absorbing more. And so this is just a quick model experiment that Gabrielle Bormann did. The yellow lines are fire, and in this modeled snowpack in the Illilouette and Yosemite, you can see after a fire that we definitely see this increase in snow in the forest during the accumulation season. And so I'm specifically interested in what happens in the Upper San Joaquin, as we've been talking about this whole time. Many of you know that the Upper San Joaquin is one of the 5 watersheds that ASO flies. It has quite an elevation gradient, and so it's not totally covered in snow during the winter, but has a fair amount of alpine. And this is in the Southern Sierras. And this is an area that has burned before, and natural burns have occurred. And we can see dating back to the 1900s that fire has smattered across this. But when the creek fire came through, the massive amount of acreage is more than this watershed has ever seen. And you can see that on the left, that it's basically overlapping with most of the other areas that have been burned. And this ultimately burned 44% of this watershed across almost all elevations. But when a fire comes through a watershed, it doesn't burn equally across that watershed. And so on the right-hand side, I developed a burn severity map using Landsat data. And you can see that there's a definite gradient from high severity burn all the way to low severity burn. And on the right, you can see how that's distributed across the area. And so definitely a lot of the area burned in this fire was in that low burned area, but we definitely have moderate and high burned accounting for a significant portion of the area that burned. And so what does this look like on the ground? You've seen this picture before from Tom, but in a high burned area, these trees are totally scorched and they're depositing visible black carbon on that snow. There's no canopy left. In this moderate burned area, there's still some canopy, there's definitely dead trees and a less visible black carbon, but definitely deposited on the snow. And the no burn sites are what we picture as a normal forest, a healthy stand with canopy and healthy trees. So this led me to ask the question, what happens to a snowpack after fire? And specifically, are these impacts of this wildfire the same across all these different burn severities? And so the first hypothesis is that in the accumulation season, the high burned areas will have the greatest increase in snow depth. However, with midwinter melt this year, all 3 of the flights that ASO flew, I would say, are considered part of the ablation season. We see significant melt happening between the February, April, and May flights. And so I'm going to focus on the second hypothesis, which is in the ablation season, I hypothesize that these high burned areas will have an increase in snow depth, a faster melt out, a decrease in SWE, and a decrease in snow albedo. And so when I took the ASO flights, I used the 50-meter product, and for February to April, we see kind of mixed results if there is any increase or decrease. But when we looked at April to May, we see a significant trend in decrease for SWE and snow depth. And I normalized this over the max SWE and max snow depth to try to account for any variation. And so we see this trend when we look from February to April as a significant decrease. But when I dug into the station data, both at a medium elevation, Huntington Lake, which is where we did our field work, and a higher elevation, Kaiser Point, which are both in this watershed and both unburned areas, what we see is that between the February and April flight, we definitely had a snow accumulation event, which maybe is why that the February to April, we don't see much change or inconsistent changes. But from April to May, we see a significant decrease, and there's a couple of accumulation events, but they're not significant enough. And that's why we see that stark change from April to May at both high elevation and low elevation. And when we look at the SWE from the station data, between February and April, we actually missed peak SWE. Peak SWE came early this year. It was a fast meltout, and that happened around the end of March. And so when we compare February to April, we don't see a consistent change because they're nearly the same when it comes to SWE. But you can see this large decrease of SWE, which explains that trend that we see between April and May. And so this is good background when we look at what happens at these different burn severities. So I then took the ASO data and I broke it down by burn severity using the Landsat data. And what you can see is that in these high burned areas, we have much less snow than we have in the no burn or even in that low burn. The low burn and the no burn definitely are more equivalent to these moderate and high burned areas. And this is February, and we can see that this continues to decrease as we move from April to May. And in May, there was barely any snow left because of the low snow year in this basin. And so what we're seeing here is that we can't treat all burn severities as equal. We can't just say burn or no burn, but that there's actually nuance between these. And this is pretty consistent with our field data. When we went out and collected snow depth while the ASO flight was flying over, we see that the no burned areas definitely have a lot more snow comparative to the high burned and even the moderate burn, and there's a general trend downwards. And so when we looked at SWE, we see a pretty similar trend. It's probably not as stark as the snow depth, but in general, this no and low burn are going to be closer than this high and moderate burn. And we're going to see more of that as we go into April and May. And when we looked at the albedo, we saw a little bit of a different trend. So on the right-hand side, we have modeled albedo from Styles et al. 2018. And what you can see is that we took measurements from February to April using a spectrometer in the field. And that should fall within these kind of blue to little bit of orange area. So the snow at that time being undisturbed should have a pretty high albedo in the no burned area. And when we compare that to our field measurements of the moderate and high burned area, we can see that it significantly drops in these areas. And what I think is interesting is that we don't see that April high and February high were our lowest values, but rather we see as that ablation happens in the snowpack that the moderate and high April values are much lower than the February and high. So we see a difference between moderate and high, but we also see a difference between February and April as that snowpack is melting out. And so this can definitely have an impact on the albedo decay over time in these burned areas. And a lot of this can be explained, I think, by the black carbon concentration. So we collected snow samples in the no burn, moderate burned, and high burned areas and brought that back to the lab and processed it. And you can see that this April high burned area has a massive amount of black carbon in it comparative to really any of the other plots. And you can see that the February high burned area black carbon concentration is pretty equivalent to the April moderate burn, which is, again, during the ablation season, that's becoming, the black carbon is becoming more powerful in the melt. So what does this all mean? We have a gradient from high burn to, or unburned to high burn, and it's definitely not the same across all these areas. And so in these unburned areas, we have more snow depth, more speed, and higher albedo, whereas in these high burned areas, we have less snow depth, less SWE, and less snow albedo. And so the way I'm thinking about it is that for now, an increase in burn severity is leading to a decrease in albedo, a decrease in snow depth, and a decrease in SWE. And between these three variables, I hypothesize that that will affect our melt rates of these snowpacks and ultimately peak flow and summer stream flow moving forward, which will lead to a decrease in water availability. So these forests after a burn are not going to hold as much SWE or snow depth and definitely impact the amount of runoff in spring and summer. And I think what's important about this is that we do need to take this into account into our models as we predict how much water is going to come from our snowpack, because it's definitely altering how our snowpack stores water and the timing of that water. And so in the future, I definitely want to take this research and add more of the physiographical variables. I want to break it down by elevation and look at forest versus open. And I also want to take my albedo values and run different scenarios of that no burn, moderate burn, and high burn, and look at melt rates produced in model runs using snow model, and then assess the impacts on stream flow using a paired sub-basin approach, and hopefully eventually look at a continental watershed against this maritime. So maybe that East Troublesome Fire that ASO plans to fly. And so that's my work to date. My field crew was really helpful in collecting all these, as well as ASO for providing the data and DRI for doing the lab processing. So with that, if there's any questions, feel free to ask.
That was great. Thanks, Arielle. That's really interesting research, and I'm glad someone's out there in the Creek Fire doing this really important work so we can understand that. I think your point about having to have this information and the modifications in the models is really relevant, and we did try to do that this year with the ice snowbar model, and so this work supports that, and that's great. I think we have time for maybe one question. We are running late, but I don't want to eat into everybody's time. Let's see.
Yeah, it's like
it's a smorgasbord.
Well, it is. It's your dissertation committee out there of people you didn't ask to be on your committee, but they're asking all the right questions.
Exactly. Let's go with Andrew Schwartz's question. Arielle, great presentation. Thank you. Do you have any indication on how long the shedding of burned woody debris decrease in albedo will persist after burn in these forests?
I don't know off the top of my head, but I think that one thing that I'm interested in is understanding these impacts definitely over time. So going back year after year and seeing if we see the same impacts. We went out into the field the winter after this happened. So the Creek Fire burned in 2020. So we only have data for not even a year, just one winter. So I'm definitely interested in pursuing this longer to see if we see the same effects over time.
That's great. Are you planning to go out next year?
I hope so. This is a pilot study, and so we have to figure out funding, but I think we hope to continue to collect data.
Okay.
We'll have BSWR spectrometer measurements over the area. So not just to the near infrared, but all the way out to the shortwave infrared. So
yeah, that'll be awesome.
Great. Well, Dan, you can have a quick question if it's quick.
Yeah, it should be quick. Yeah, my question is, do you have any insight into the physical mechanism by how the carbon actually gets into the snow? Like, does it require a wind event to flake it off of the burned branches, or does it happen when the snow falls through the burned canopy, or can you tell?
That's a good question. I can only speak anecdotally from my own experience, but these trees are so fragile that I think that they just are breaking down and just shedding into the snow. I don't think it takes much disturbance to make that fall. But I don't know. I don't know fully.
Great.
Thanks.
Thanks, Arielle. That was awesome. There's a few questions in the chat. I would really love it, Arielle, if you could respond to some of those. That would be as best you can. That would be super great.
Also in the Q&A.
Yeah, absolutely.
Yeah. Okay. Next up, we have Reggie Walters. He's from Hetchy Water and Power. They've been obviously focusing on the tuolumne. These guys have had data for 9 years, ASO data for 9 years. So Reggie's had a good time. And so I'm really, the point is they've been working with this data for a lot longer. And so I'm really excited to see how their applications have evolved with more and more years of data as it comes through. Okay, Reggie.
Thank you, Kat. Can you hear me and see my slideshow there?
Yes.
Okay, great. Thanks so much. And thanks, Liz and Tom and the rest of the ASO team for hosting the event. It's nice to be here with you all. So yeah, as you mentioned, we have a lot of data here at tuolumne. I've been here for just a few of those years, but yeah, it's a really great data set to try to piece through on our end. So I'm going to talk to you all today about ASO applications for some of our operations here at Hetch, Hetchy Water and Power. And while I'm the one giving the talk, you know, there's a lot of people responsible for the work that has gone into some of the stuff that I'm going to show you today. So just want to acknowledge my coworkers, Chris Graham, Harrison Forrester, Nick Welty, as well as our student intern, Grant McNamara, and then Bruce McGurk and Roger Picklum, our former employees, who have also contributed to some of this stuff. So I will start my talk just by giving you kind of an overview of our system, and then I'll talk about some of our modeling efforts where we use the ASO data both empirically and also to constrain and inform a runoff model that we're using deterministically. So the SFPUC, the San Francisco Public Utilities Commission, is responsible for delivering water to about 2.5 million people in the San Francisco Bay Area. And Hetch, Hetchy Water and Power is a division of the SFPUC. And we supply about 85% of their water. So the vast majority of it comes from Hetch Hetchy Reservoir, which is shown on the right-hand side of this map here. It's inside Yosemite National Park, as everyone's probably aware. All the water that we divert for deliveries to the city passes through 2 powerhouses along the system. The upstream most, which is Kirkwood Powerhouse. And then once the water leaves Kirkwood, it goes into another tunnel, goes to Moccasin Powerhouse, and then it traverses the San Joaquin Valley, Central Valley, Coast Range, and ultimately makes its way to the Bay Area, all via gravity, which is pretty neat. And so, every drop of water goes through a powerhouse. It actually goes through 2 powerhouses, and when we have excess water, we can generate additional power draft with that water. So here is a look at the reservoir itself. We're looking kind of upstream over the spillway. You can see Wapama Falls in the background there. And this was taken in summer of 2019, a pretty large water year. And this is kind of what our group hopes to achieve every year, is to get the reservoir up and full and spilling over the top of these drum gates in the spillway. So we like to exercise that spillway channel within constraints every water year. And we, given adequate water supply, we can make that happen. And along the way, as the reservoir is on its way up, we're of course managing all those inflows via power draft and valve releases to the river downstream. Our annual average inflows are about twice the storage capacity of the reservoir. So in a normal year, we're passing a lot of water, whereas in a dry year like these past couple, it's been significantly more marginal. But in order to make this happen efficiently and optimally and safely, we're of course relying on forecast products. So here's a look at our traditional statistical model. This is the evolution of that model for this past water year 21. And you can see in this funnel plot the median forecasts, which are indicated by the black diamond or circle figures there, just steadily declined in response to persistent dry conditions up country. And our April through July runoff volume came in at about 230,000 acre feet, which is about 40% of normal. Here is just some sample output from this particular model. that's derived from principal components, regressions. And we can see that our April 1st forecast just barely captured our observed outcome at the very lowest exceedance quantile or percentiles. So it's like probably a 97% exceedance in this particular model output. Whereas, usually on an April 1st forecast, we're landing at a wetter outcome in the model. So we were taken by surprise as the runoff season kind of evolved, as I think a lot of operators in the state were this year. So we're well aware of the potential for and probably the ensuing breakdown of some of those statistical relationships that we rely on. And the ASO data is probably the most powerful tool that we have available. We use a lot of different tools and a lot of different data products, but the ASO is becoming probably the most powerful one that we have at our disposal going forward. And as Kat mentioned, we have 9 years of data in the Tuolumne, so we're really fortunate that the program was sort of piloted here. By my count, I have 64 GeoTIFF SWE maps. I hope that's the right number. You guys can correct me if I'm wrong. You're going to see this time series on the bottom just showing how we've captured a range of very dry years and some very wet years as well. So there's a lot of variability in there. And it's only being expanded. So now we actually have SWE data above the other reservoirs that we operate, Cherry and Eleanor. And then last year, I believe last year was the first year for the full Tuolumne. So the entire watershed above Don Pedro Reservoir, which is operated by our friends at the Turlock and Modesto irrigation districts. So here's a plot that's probably familiar to a lot of people here today. This is what some folks I think are calling the Graham plot. And so my supervisor, Chris Graham, first kind of looked at this relationship, very simple relationship between Airborne Snow Observatory, SWE above Hetchy Reservoir, and the inflows that would come off or that would arrive in the reservoir from that date through the remainder of the runoff season. And he found a pretty tight relationship between those two variables, especially when you filter for flights after which there was some non-trivial amount of precip. So the filled in markers here are flight dates after which there wasn't very much rain. You can see that if we do get spring rain events, it does cause a divergence off of this one-to-one line, as you might expect, although sometimes the direction with the divergences are not in the direction that you would expect. So we could take that a step further and build this like empirical regression model where we include precipitation as an explanatory variable. And we tighten up that fit a little bit. So now we don't have a one-to-one line, but we just have a simple multilinear model where we include the ASO data and then the precip. And we can see the two flights we got this year, Feb 25 and April 29, fall pretty close to the line, particularly the April flight. The February flight was a head scratcher. It fell way off the line. And you can see on this panel on the right, we can attempt to do something similar to what Eli was showing us yesterday, to like resample from historical precipitation distributions to try to come up with an AJ forecast from the ASO product. We can see that in hindsight, the Feb 25 flight, we overestimated runoff, which is shown cumulatively on the black line here. But for April 29th, we landed pretty much right on the money. So yeah, I won't say too much more about that. And again, Eli gave a really nice talk yesterday where he is, taking this 10 steps further by addressing some of those other variables at play here, like perhaps the demand for water in the soil column or in the atmosphere. So I'll shift gears for the rest of the talk. I'm going to talk now about our internal runoff model. We have a PRMS model that has been calibrated for the Tuolumne River above Hetchy. And it's a USGS product, and we heard a little bit about it on Monday, so I won't go into too much detail about how PRMS works, but it is a distributed model. And I believe Bruce McGurk did the delineation of these hydrologic response units, or HRUs. So we have 280 of them in the model, which we feel adequately captures a lot of spatial variability. It's obviously much coarser than ASO, but it does distribute variables and parameters across the watershed. And Chris Graham did a really nice job calibrating the model. We are working on a bit of an overhaul right now, calibrating, but we feel that it does an okay job of representing snow accumulation to some extent in the basin. And here's just a comparison with some pillow data for the past few water years to either convince you or not that the model is doing well, depending on which subplot you choose to look at. But nevertheless, no matter how good we do, the model is always wrong. And we now have observational data available to us at really high resolution and accuracy from ASO. So if we take the ASO data and resample it to the HRU resolution, we're now ready to dump that data into the model, and we're trying to do what everybody else is doing, which is this direct insertion data assimilation into the runoff model. And we've had what we think is a little bit of success with this for the past couple of water years. So yeah, on the date of an overflight, this, we can kind of skip over this slide. It's just meant to trick you into thinking we're doing something really complex. But on the date of an overflight, we just update the model SWE state with the observation from ASO. And you can see in this time series here, it either bumps the SWE state up or down, depending on differences between the model and the observation. But it's important to note, we're not just updating the SWE on the basin scale, we're updating it on every individual HRU. So we're able to redistribute the snow according to what ASO sees. And then we can restart the model and allow that evolution to kind of play out from that point forward. And then the logical next step, of course, is to turn that into an inflow forecast. And that's what we're interested in, of course, as reservoir operators. So we want to take our model and run an ensemble forecast so that we can plan on, the order of weeks or months ahead with some uncertainty bounds that we hope captures our observed outcome. And so here we're looking at a May 7, 2020 ensemble forecast. And so we just spin our model up, read a restart file on that day, and then just like what, or similar to what the RFC does, we just spin the model forward a whole bunch of different times by resampling from climatology. And if we update that initial condition with the observed ASO data, we can see that it changes our runoff distribution fairly significantly. And then we can see if in hindcast kind of what the results look like. So the black dashes are our observed runoff for the remainder of that season. And then we can add one more ensemble member, which is our hindcast member with the observed weather data from that year forced through the model. And the model that has been updated with ASO, which I'm plotting in red there, it gets nudged towards the observation from the open loop model. So that's encouraging to see that, it's pushing things in the right direction in this particular forecast. So if I turn that on its side and show you that in cumulative terms, here's that same ensemble forecast. And I'm sorry, I think I changed the color scheme here. So the red is now the open loop cumulative runoff from that date forward without any ASO information ingested into the model. And when we compare that to our observed runoff that we got for the remainder of the April through July period, we can see that we over forecasted inflows somewhat dramatically. Even our driest member over forecasted inflows. So this wouldn't have been a forecast that would have panned out very well had we operated to it. We can see that if we have a forecast that's been updated with the ASO information, we get closer to the truth, and our uncertainty bounds capture the outcome, which is promising. A few weeks later, last water year, we got a flight on May 21st, and you can see here similar behavior in the model. We feel that it probably just had too much snow simulated in the watershed in the open loop simulation. And I'm now showing the update on May 21st. This is not a sequential update. I'm just running open loop up until that flight and then updating. And we can see that basically the driest member matches our observation fairly well there for that forecast. So where the rubber kind of hits the road for our purposes is taking an ensemble forecast and then dumping it into some kind of decision support operations projection. And that's what I'm showing you here. So this is one of the things that we looked at when we were getting ready to fill the reservoir in 2020. So on May 21st, we had about 335,000 acre feet of storage. That was our initial condition for this model run. And our maximum storage is just over 360,000. And our power draft at that point in time was maxed out. So we were just kind of trying to maximize revenue via power generation. But we want to fill the lake kind of at all costs. That's our primary goal. And at some point we needed to make the decision, okay, when are we going to back off power draft and drop down just to our baseline water delivery rate, which was about 400 CFS at this point in time. And so this gave us, by the way, this is forced with that PRMS ensemble forecast that has been updated with ASO. So if we look at what actually happened, we were looking at all the available information and all the models, but what we actually did fell within the bounds of this projection. So again, this is really encouraging, and it's looking like a pretty promising path forward. And now I'm going to go quickly, just for the sake of time here. Here's just a look at some forecasts from this year, April 29. As I mentioned, we got an ASO flight. Here, I'm just comparing with a couple of other forecasts. So one from the RFC and then one from our internal statistical model. We had a decent amount of disagreement here. But again, the ASO at this point in time pointed us in the right direction to say, hey, you might be headed towards a drier outcome than your other models are indicating. And if I look at that same operations model that was spun up on April 29th of this year, it was kind of giving us a very different results. So in the top panel, I'm showing that ops model with the ensemble forecast that did not have any ASO information. And in the bottom, we do have the ASO update. And we can see in the top one, it's saying, okay, you're going to fill in every scenario, and you probably have some additional power draft available at your disposal. But ASO is telling us, hold on a minute, you don't have as much snow runoff, somewhat runoff remaining as you think. And even if you leave your power draft minimized from here on, you still might not fill the lake. And that took us a while to kind of wrap our heads around and accept, and it was a bummer, and we didn't fill Hetchy this year. But we did fall much closer to the simulation, in this case, that was forced by ASO, as you can see here with the observations plotted in blue. So yeah, it's proving to be what we think is a powerful tool for our operations. And I'm showing you some success stories here. So I should probably leave you with this last couple of figures, which is more of a defeat, perhaps, where earlier in the year, we were still seeing these way wetter outcomes, regardless of what forecasts we looked at. So here's a forecast, or here's just a deterministic simulation of the water year. And the open loop SWE simulation is plotted in the solid line. And I'm updating the model with the Feb 25 flight in this case. And we could see that the model was actually doing fairly decently, which was promising in terms of snow accumulation as compared to ASO. However, when it started melting that snow, it was just way too efficient. It was producing way too much runoff, way more than we were observing. And this to me highlights a couple of things. The first of which is just the need for improvement to our model. We're not addressing, whatever was causing that missing snow that everybody's talking about, which, was potentially lost to very, very dry soil column and evapotranspiration and sublimation, perhaps. So we're continuing to interrogate these issues. But it also highlights to me the utility of the April 29th flight that we got this year that kind of put us back on track. So we were really fortunate and thankful to have that flight. So I'll leave you with this picture of the Horse Meadow Met Station snow depth sensor as we found it in February this year, which in my mind highlights the importance of remote sensing observations of snow when instruments fail or get blown over by a windstorm, which is what happened here. And I'll be happy to take questions in the chat, or you can email me, or I can take them now if there's time.
Thanks, Reggie. That was a really great talk. It was really compelling, and so much so that Tom has come over
to the other side of the table just to say I got chills. So thanks for that. That was an awesome talk.
Yeah, that was really great. I see Joe has his hand up.
Yeah, and there's one in Q&A. Mine's real quick. Obviously, it's fantastic to see it in use, like you said, where the rubber's meeting the road. And ultimately, can you just briefly say something about return on investment, or what that, if you had gone with the non-ASO update, can you quantify the losses in a dollar amount or some other way? Because I mean, it's great to know that it helped, but I'd love to know how much.
I can't off the top of my head. I mean, if we had just brick and mortar, like trusted the most bullish forecast we were looking at, I mean, I think it would have cost us something like 20,000 acre feet of storage that is now in the reservoir that might have been drafted via power generation. I can't say off the top of my head what the worth of that water is, but it far exceeds the revenue we would have generated if we had dumped it through a powerhouse.
Yeah,
that's great. I'll take Gus's question. Reggie, do you have any hindcast comparisons back through 2013? And also, do you have any concerns about the direct insertion method?
Sort of, and yes, are my short answers. I have a script in progress to do that hindcast comparison. So there is a little bit of, and I guess those two questions are kind of related, or my answers to them will be. Maybe I'll just answer the second one more thoroughly. Yeah, I do have problems with it sometimes. The larger the discrepancy between the snow-covered area in the model and in the observation are, the harder time the model has ingesting that information. Because if we had like a false negative HRU that thought it had already melted out its snowpack, but then on the ASO flight date, we try to rebuild a snowpack on it. We're having to assign all the other ancillary variables to that snowpack. And the model doesn't like that very much, so we have to kind of spend a little time treating that as carefully as we can so that it doesn't break down. And so that makes the hindcast part of it, to do it in one fell swoop, in one giant loop, I think it has to be treated on like a case-by-case basis. So that part is a work in progress.
Good points. Thanks again, Reggie. That was really great.
Thank you.
Yeah, for sure. We're going to skip along. We've got HP Marshall up next. He's from the Boise State University, and he's going to be talking about radar, InSAR, L-band, and using that information to infer the snowpack in general.
Great, thanks, Kat, and thanks to the ASO team for the opportunity to present to you guys. Can you see my slides and hear me okay? Just put it in full screen mode here. Great, well, yeah, we're gonna shift gears a little bit. I've been fascinated by these talks about how ASO data is being used for operations. I'm gonna share a little bit with you about how critical data sets like those that ASO produces are crucial for calibration and validation of other snow remote sensing techniques that we're looking towards for spaceborne applications. So a fairly long list of co-authors here, more folks working on this problem as well, and I'll share you some of those details today. So just a little outline, why are we interested in low frequency microwave radar for snow? I'll talk a little bit about how it's a measure of the time of flight to the ground through the snowpack, sort of similar to the time of flight to the snow surface. How we
just a quick thing, we're not seeing your slides advance.
You're not okay. Let me try stop sharing.
On the first page. Sorry to interrupt you there.
No, thank you. How about now?
Yes, that's it.
Great. Yeah, so I'll talk a little bit about why we're interested in this specific frequency, how we might use InSAR phase changes to estimate snow change. So InSAR phase changes are normally used to measure the deformation of the Earth's surface after earthquakes and volcanic eruptions. But that sort of approach of looking at the time of flight to the surface can also be used to look at changes in snow cover because the snow slows that signal down. I'll share with you just a little bit of results from the SnowX 2017 campaign, where we first kind of started looking at this in direct comparison to ASO data, both a machine learning and a physics-based approach that we've tested for retrieving the change in snow depth, and then kind of where this is going with the large time series of InSAR that was collected in 2020 and 2021, and some further comparisons with ASO data, and then some conclusions. Did you see that advance? Look okay. So the reason this low frequency microwave has potential for snow is that most of the efforts for using radar from space for snow cover observations have been focused more on much higher frequencies. They are sensitive to changes in SWE, but they're also really sensitive to snow microstructure. So that's one complication, is that you need information about snow microstructure. So we're testing this much lower frequency, or 1 gigahertz, 24 centimeter wavelength, that's so much bigger than the snow grains that it's more or less insensitive to the snow microstructure. And there's some promising snow depth and SWE change signals that we're seeing. The reason we're not proposing this for a new satellite mission, but NISAR is a US Indian satellite mission that launches in January 2023 that will have one of these L-band 1 gigahertz InSAR systems on it. And the ROSEL is another satellite mission that's moving forward with the European Space Agency. So NISAR in particular is the one that launching in 2023. It'll have global coverage, 10 to 50 meter resolution, and a 12-day repeat. But it is going to require fusion with other models, observations like ASO, and in situ observations. It's not the sort of holy grail for snow information, but it's one piece of the puzzle, I think. So just this slide from Mark Raleigh, just showing how there are pluses and minuses between the various pieces of information that we use. And again, the L-band InSAR approach is not going to solve all of our problems, but it's complementary to other techniques such as lidar, optical snow-covered area, albedo, and volume scattering from these higher frequency radar approaches. And it will require some in situ observations and models, but hopefully I'll show you today that there is information about snowfall events that I think is useful. So the basic idea of using L-band InSAR is that we've been using the travel time, the time of flight of radar signals through snow for quite some time from both mobile and tower-based platforms. This work goes back to the late 70s, where people used ground-based radar systems to just measure that time of flight between the radar system and the snow surface. And because it penetrates through the snow between the radar and the ground, and using that time of flight through the snow, you can estimate snow depth and SWE. This works really well in a dry snow scenario. So we've got tower-based systems that do this well when it's dry, but there's challenges when the snowpack starts to get wet. So again, this is a technique that I think has a lot of advantages for dry snow conditions and for helping us understand the accumulation season. This is just a little sketch that was first proposed by Gunnarsson et al. In 2001. And so this is the basic idea. We're measuring a signal that goes down through the snowpack. The snowpack's relatively transparent. That signal bounces off the snow ground interface and comes back. And while it's moving through the snowpack, it's moving slower. And what controls that speed is the density. So we have to do two things. We have to deal with that change in speed and then the refraction at the snow surface. But both of those things cause a change in the travel time that's related to the density and the snow depth and SWE that's on the ground. So a little bit of data from what we collected in 2017. So there's been some work on this, but the current spaceborne L-band InSARs have repeat intervals of 45 to 90 days, so not very useful for snow in the mountains. During the 2017 NASA SnowX campaign, we flew InSAR several different times with much shorter baselines. So on the left is the phase change that was measured by this Airborne InSAR over about a 2-week period, about 16 days. And on the right is the total snow depth from ASO. So you can see there's some similar patterns there. There's some relationship between this phase change and total snow depth. On the bottom two figures are the amplitude from this radar system compared to the ASO vegetation height. So picking up similar differences with the tree islands versus the open areas. So the first thing we wanted to start with was just a simple statistical approach. So we did a machine learning approach, a simple random forest, to see how well we could predict snow depth from the measurements that were made from the airborne radar. So the inputs into this machine learning approach were just what was measured on the aircraft, which was phase, coherence, amplitude, and incidence angle, really phase change. And really, this wasn't the direction that I see application, because you'd have to tune it to a big data set of snow depth. And if we already have the ASO snow depth, maybe this doesn't add a lot. But we wanted to make sure that our physical understanding that as the snow depth changes, we get a change in phase was correct. And the variable importance, sort of how well each of these things predicted snow depth, phase was by far the most important one. And so that just confirms that there's not a big amplitude change, that the snowpack is relatively transparent at this frequency. So just another comparison, we're zoomed in at just about a kilometer by kilometer area. And on the right-hand side is the ASO total snow depth. And you can see this is a place where there's big drifts and scour regions. We're looking at 0 to 2 meters in a small distance there. And on the left is the UAVSAR phase change that was measured. You can see some of the same patterns. The machine learning sort of approaches on the lower left. On the lower right is just the phase change versus ASO snow depth. And you can see a pretty high correlation there. Again, this is just the reason there's a correlation is not that the phase change is measuring total depth, but as we know, these snow patterns tend to repeat. So if these patterns are repeating, then snow depth should be related to change in snow depth for a given event. Again, now moving to that physics-based retrieval where we take into account the incidence angle, we use an estimate of the snow density on the ground, and we retrieve the InSAR depth change. That's what I'm showing you on the right. On the left is the ASO total snow depth, and this is draped over the terrain, which is exaggerated here, mostly just to show you that we have deeper snow on the lee side of these terrain features. The wind's blowing from the right to the left here. and we see phase changes that are increasing our estimate of the amount of snow in these same lee sides of the terrain features and scouring on the windward sides. If we do this over a much bigger area, again, now this is the UAV SAR L-band depth difference retrieval from 0 to 25 centimeters. So it didn't snow that much, just 25 centimeters in the deepest spots. But compared to the ASO depth map, you can again see similar patterns. One of the challenges with this 2017 campaign is the InSAR was kind of tacked on at the end. The effort was really designed to measure the spatial pattern of total SWE rather than the change in SWE. So this was just our first glimpse into whether this technique might provide some useful information when these satellites do launch. And just keep in mind, again, we only saw about an average of 10 centimeters of depth change. But we do see this kind of east to west trend in the snow depth change that agrees with the east to west trend in the ASO snow depth map. So from there, we decided this was promising enough that we wanted to do a fairly comprehensive time series with L-band InSAR. So this is an aircraft. UAV SAR is a terrible name. It's not on a UAV, it's on a Gulfstream and flies at 40,000 feet. It is owned by JPL, and so they took off from Pasadena and flew all 13 of these sites in one day from the Gulfstream. And so in 2020, we flew bi-weekly every 2 weeks, and we did 6 campaigns over 13 sites. And then we're shut down due to the pandemic. And then in 2021, we did it more frequently. So we flew every week, 10 different times over 6 sites. And we had local experienced field teams that deployed on the date of each overpass. And then ASO flew over subdomains at a subset of these sites. So again, we were trying to capture a range of snow climate and a range of conditions and topographic situations as well on the ground. And this is looking at a similar area on Grand Mesa. So now we've got the UAV SAR inversion for the depth change on the left. And this time ASO had data products for 2 flights that spanned the UAV SAR pair really well. So they were within a day of each other. So this is over about a 2-week interval. This time it's 12 days. But what you can see on the right is the ASO depth change. We're getting scouring to 25 centimeters and drifting to 25 centimeters. So not a big change in snow on the ground, but patterns that agree quite well with the estimate from the InSAR of the depth change. So this is over a 2 kilometer by 2 kilometer region. We did use the field measurements of density to estimate the wave speed, and we're seeing these drifting and scouring patterns. There's only one tunable parameter in this inversion. The phase shift, you have to kind of pin it to a specific point. But so it's just a constant shift that you apply. But once we apply that shift, then the patterns agree quite well, and the dynamic range agrees quite well. So this is different than other radar approaches where you have many sort of tunable parameters that have to do with the microstructure that's existing on the ground. So just a comparison of the histograms here. So again, this was between February 1st and 12th. ASO data on the top histogram and the UAV SAR L-band InSAR depth change on the bottom. Those shapes agree pretty well. And then just the scatter plot on the right there of the ASO depth change versus the InSAR depth change. A root mean squared error on the order of about 5 or 6 centimeters of depth, or on the order of about 1 centimeter of SWE. But I just want to clarify that this is showing promise in dry snow, in flat terrain, and in open areas. Now, that's not the places that many people on this call are interested in, but we are going to start getting this data every 12 days at relatively high resolution. So it's something that could be integrated with all the other tools that we tend to use. And again, this is several years out, but just giving you kind of a preview of what other sources of information might be on the horizon. So this InSAR approach for measuring snowfall patterns is showing promise. For the Grand Mesa InSAR retrievals that we've performed so far from 2017 and 2020, it's showing strong correlation with lidar. We did this really large time series in the Western US, and we're in the process of analyzing and processing all of that data to characterize the impact of vegetation, topography, wetness, and snow climate. I will say that I think the use in dense forest and in saturated wet snow is unlikely. Jack Terracone is a student of Ann Nolan's. He's seen some really exciting results, even in somewhat wet snow in the HMS River. But I will say that we typically don't see this working when the snowpack is completely saturated. In some ways, that makes it a little bit, suited nicely to be combined with lidar, where this would be much more focused on the accumulation period, and then you'd need to move to other techniques for the wet snow period. So again, suited for mapping snowfall in open areas, and still a lot of work yet to be done. So this is still preliminary, but I'll stop there. Happy to take any questions, and thanks again for the opportunity.
That's great. Thanks, HP. That was really great. And it's always good to get ahead of what new sources of information are going to be coming out. And so linking this great work with NISAR and everything is really useful. We've got a couple of ASO folks with their hands up, so I'm going to preferentially choose them. Go, Jeff.
Thanks, HP. Great stuff as always. You mentioned the conjunction with LiDAR for maybe mapping during different time periods. What about coincident conjunction with LiDAR? Is there any advantage to be gained by pinning the LiDAR, snow depth with LiDAR, and then extracting other parameters with the L-band signal?
Yeah, that's a great. We haven't made it far enough along that route to show some results, but it's a direction we're going. If we constrain the snow depth, and then we measure this time of flight through the snowpack, if the snow's dry, there is this potential for inverting for density. If it's wet and you have some idea of the density, there's a potential for getting some information about liquid water content. It's a little bit tricky from the phase change. We're seeing some good results using ground-based radar combined with LiDAR to map snow density. The phase change is really the change. So you'd be measuring the change in density. So we still have some work to do to kind of figure out how we would result in a total density, but it might be something that could be integrated with a model to help understand time periods when density is decreasing or density is increasing, and helping to constrain that. Great question.
Awesome, thank you.
Yeah, great question. I find that piece particularly exciting. Evan, got a question?
Mine's pretty simple. Like what baselines are you looking for between flights?
So the temporal baseline that we've been targeting is what NISAR will be, which is 12 days. The ESA Space Agency is going to be more like 6 days when that eventually launches. That's like 2026 or 2027 at this point, I think. So we're kind of testing like 1 week to 2 week intervals. When we go beyond, like when we get out to a month or more, we lose coherence, and you kind of lose that phase information at that point.
Okay, what about the physical baseline on the plane trajectory?
Yeah, so this is a little different than like a topographic mapping approach. You're trying to keep that physical baseline as small as possible.
Yeah.
So the aircraft flies within a 10-meter tube, they call it. They get that flight plan within 10 meters.
10 meters, wow.
You can adjust for that. I mean, there's a residual baseline correction that you can apply, but the goal for this temporal change is really
nice and tight.
Yeah, nice and tight.
Okay, cool.
Good question.
Well, thanks. This is awesome.
Yeah, one quick question from me, HP. Well, actually from Tom. What's the expected lifetime of NISAR? Well, how long do they think? How long are they planning the mission for?
Yeah, I think it's like most satellite missions where they often plan for more like 3 years, and then they sometimes last a really long time. They're in the process of planning NISAR 2 already. Rose-L is going to continue. Some of these other NASA mission concepts are also looking at L-band InSAR, and the Japanese Space Agency is moving forward with a new one too. So I think we'll have some form of L-band InSAR moving forward in the future. But what that looks like, I think, is still to be determined. Great question.
That's great. That's great for the operational implementation down the road, and just the supplementing of our program. So
yeah,
that's great to know.
Absolutely.
Thanks, HB.
Awesome. Thank you, guys. Appreciate it.
Okay, moving on to Marco Bell. Marco used to be with the Merced Irrigation District. He's now moved on. He's a consulting engineer, but he's still very deep in the water, pun intended, resource industry, and he's going to talk to us about using ASO and some modeling in the San Joaquin.
Hello, everybody. Thank you for this opportunity to talk. And I'm going to try to make mine quick in the interest of time here. So this is a little bit about me. When you tell me I can't do something, I think of Tommy Lasorda, I say, yes, I can. So I've been working very hard on trying to implement what I consider sometimes impossible, but we try to reduce the variability and the uncertainties into our runoff forecast, into reservoirs, and try to make some kind of a decision tool so that managers can operate the reservoirs. I've been working very closely with a lot of people that are here today. And Steve did an awesome shot earlier today that talks about the kind of decisions we have to make as operators. There's been 2 implementations of these what I call H2O models. The first one was done in Big Creek a while back. We got very lucky to be able to implement that. Then the second one was with MID at the Merced Irrigation District. The Big Creek one, you can see the areas in blue are basically the snow areas. And you can kind of look at where all the different glaciers are and some of the ones that we were implementing. It's a very complex system, as you can see, but we were successful at implementing the model and starting to take a look at the snow. And this was provided a basis for the next one. Oh, this is the HMS that resulted out of that effort. And I got to give my a shout out to B-Big because he's here. And him and I were down in the weeds putting this together back then and working very hard day and night. Then I went and transferred to Merced Irrigation District, and they'd say, Marco, we need help with the checker inflows. It's basically the same issue, taking a look at the snow. Fortunately, we were able to touch bases with Tom at one point, and we're now implementing, with the help with Stephen Ho, who's also here, of taking a look at the ASO data and try to put that into the MID H2O model. And as a result, it does perform enhancement. This is basically the HMS model component for Merced in the Upper Basin. One of the things that we learned very quickly is that we have to take a look at the parameters that are very sensitive. And to do that, we have to address them very carefully, which usually means having a spatial and temporal discretization that is significant. Here you can see that the PX parameter, we call it PX, but it's basically the temperature at which the precipitation will fall either as rain or snow. With a high PX value, for example, 38 degrees here, you can see that a lot of it falls as snow and less becomes runoff. With low, you can see that a lot of it ends up falling as rain and less as snow. But look at the difference in flow that you get, and this is on the Upper Basin. It can be as much, 16,000 CFS, that's 32,000 acre feet in one day. These kind of differences are important when you're trying to make a decision on how much water you're going to release out of the reservoir, when is the water going to get there, how much is going to get there. So we decided to basically grid this kind of data, which most models do not grid it, and we're able to kind of work with the models to try to do this. I think to reduce variability and reduce the uncertainties in a model, this is the kind of thing you have to do. You got to identify the sensitive parameters, and then you have to get a detailed look and integrate that into the model. And I think that's what ASO does. You go out there, you take this flight, you get a gridded data set. And the gridded data set looks at the variability in the field from grid to grid of what the snow is. And with the ice normal model, you can get the sweep. Well, that kind of data goes directly into these models. And from that, we're able to correct the drift that you can see in the sweep from the basins. And that's very important to do And without the aerial variability that we get with the ASO snow data, this is very difficult to do. And with time, this does drift, and you don't get the right answers when it comes to runoff without this correction. Here's an example of the decisions like operators have to make. This happened in 2017, and we had 2 peaks that year. You can see that there's a very high level peaks here, but in this peak, we decided to release early. The models were telling us, you know, we can release enough, we can hold another 50,000 acre feet. And you know what 50,000 acre feet can do to operation is a big difference. The variability that we have, however, did not provide the confidence to the decision makers at the time. Okay, so if we can reduce that variability on the snow and say, yeah, we can get down to 10,000 acre feet instead of 50,000 acre feet or 100,000 acre feet, then we can make decisions that are going to be beneficial to the water supply, to flood control, to the environment, those kind of components, you know, in the decision makers have to make. I'm sorry, I don't know if you see that. I think I froze with that. Give me a second here, please. We also talk about how automation and optimization is important. But I like automation and optimization because then it produces a process where you can couple this, you know, with other kinds of in the systems. We're not just managing snow. That snow actually impacts everything we do, every decision we make, and it starts at the very top with the snow. The snow melts, it comes down into the groundwater, it comes down into our reservoirs, and it comes down into other programs that we can do. It impacts the environment. You know, how much water do we release to maintain the reeds for the salmonoids, you know, safe? And you know, how is it going to guide our research? How are we going to integrate that with FloodMark? And do things like climate change and fighting climate change. And there's answers to that, actually. And it all starts with this process. If you automate it, you can couple that with other models, and that was our original intent. Back in 2013, I believe, you know, almost not quite 10 years, but we had this vision. We created this chart back then, and you can see that we wanted to optimize the data systems in the area. And that includes everything to the irrigation, groundwater, and of course, it all starts in the upstream, and we have to get this part right. You don't get that part right, the rest of it becomes, you know, just an exercise in computing. But yeah, this is the vision that I think most operators have, is how do we manage our system, and how do we optimize that system? One of the things that we had to do is we took a look at the snow. Okay, so from the very start, we knew we had to get the snow right. And a lot of our models that we had before weren't gridded at the time. I mean, you know, you get lump models and you get a kind of QPFs, you know, that are 6 hours or stuff like that. And we wanted to get a time increment of 1 hour to catch a lot of the changes in the storms. And we wanted to be able to manage what's happening at the snow level. So Custom Weather, this is their model. They have what was called a surface layer model. And from that, they look at all the different forecasts that were out there for precipitation. They have a feedback loop so they can see how each forecast is performing. And then based on that, they're able to weigh it. You know, it's a little bit subjective, but it is based on performance, past performance. It requires high terrain data. So we're able to take things, we're able to consider things like topography. Big deal at a fine level, fine resolution. And from that, they're able to do an energy balance at the surface. So we're able to know what's happening in temperature at the surface layer of the snow. And that helps us get our PX value correct. Okay, so put that together with gridded data, that really becomes useful. And I think this is kind of one of the advantages that we get, you know, from the ASO data. We're not getting these data points on the right like this. When you look at a lump basin, we're actually getting some kind of a gridded analysis, kind of you see here on the left. that we can actually utilize and get a better handle of our runoff totals. Here's an example where that data can be useful. This was our forecast, gridded data forecast for our data. And then this is after the fact, we got observed data. You can see the differences here. Well, where is the differences more significant? The higher green you can see here is the higher precipitation levels. And the bottom, the light blue and the dark blue is where there's less mist. The orange is, the really high misses. You can see that the model is actually not doing too bad on the lower elevations. But at the higher elevations, we lack data in the higher elevations. And this is where the snow flights can really, really help. We can see that with that data, this is going to become, a lot more refined and a little bit more precise, and it's going to reduce the uncertainties. If you do it on a non-gridded basis, then you really, at that point, it's really not useful for what we do in the Sierras. I shouldn't say not useful, because we can get some data out of that, but you can see that fine-tuning this really is what we need to do for the long term. How important is this? This is the average annual unimpaired volume of Vernalis, which is downstream of the San Joaquin Basin. 6 million acre feet a year on average. But if you take a look at the differential of the peak, the maximum in 83, it's 3 times as much. Okay, so we're talking very variable data. It's not something that is most of the years is going to be near 6 or 7 million. We're talking about 3 times as much water. Can you imagine what you're going to do without that water? Same things on the other end, on the drought. It's really significant. The drought, look at this year, there's not even close to this kind of amount of volume. We're now in a process where we're putting in for a grant. We're kind of working together with the ASO. We're probably going to try to incorporate some of the ESRI solutions that you saw earlier. We're working closely with Every Sardo and DWR to try to implement a HMS model for the entire San Joaquin Basin. I shouldn't say entire, from Big Creek all the way up to north of Stanislaus and that area. And this is also supported by the U.S. Army Corps of Engineers. I want to give them thanks. They're not necessarily implementing this model yet, but they probably will in the future. I'm hoping that it works because my goal is to do the impossible, to work with you guys and perform, these kind of models in a way that operators can actually use and make decisions out of it, and reduces the variability, reduces the uncertainty. It is a physically based model, and it's going to, really provide kind of the answers and solutions for decision support. And combined with the latest technology, I really hope that this kind of moves forward, and everybody's doing a great job with that. The model, as I mentioned, is going to go from the Stanislaus to Big Creek. There's no reason why we can't add other basins in the future, and it's definitely my hope. Again, this is just an HMS model. I shouldn't say just, this is an HMS model, which is the hydrometeorological systems, what HMS stands for. So basically, they're going to be looking at the local inflows. It's not going to be looking at reservoir operations, and it's not going to be looking at optimization of simulation or even river analysis like water surface elevations and things like that yet. If the individual basins want to do that in the future, they may, but I at least want to establish what I've done in Big Creek and in Merced and try to leverage that so that we can work together with the ASO and integrate these data sets in real time for people to see. It is going to hopefully be a public model once it's ready to go. And that'll be a decision that I think David will have to make in the future. I mean, Dave Risardo and his group. So we're looking at starting the data upstream with the lidar, the ASO data. We're going to do the model runs. It's going to reside at the Department of Water Resources, and then from there they can work, with like the FCO group and others. I put MID, but it really is anybody who wants to use the models that is a stakeholder with DWR, and works through DWR, to get the data sets, and maybe we'll have the data sets also in the ESRI website. Some of the parameters that I thought was very important. We talked a little bit about the px and some of these snow hydrologic characteristics that are sensitive. But the other ones are like soil moisture deficit, simulational losses in the basin. I was looking into, okay, how do we simulate that today? A lot of it is, hydrologists taking a look and taking their best guess at how to calibrate that, use it as a calibration. We haven't really done a lot with the soil moisture sensors out there. I think it's time to do some of that. I'm working with Stephen Ho and trying to get those in the Merced Basin. If the grant gets through, we may be able to do that in other locations. And I want to start doing some research on that. That's one of my goals, to take a look at how the losses are impacting runoff and how are the waters going into the base flow. How is groundwater flows acting as a reservoir for water supply in the future? And these are really difficult questions that some of the technology there is even outmoded, like the losses in the soil. We've been using the same approaches for a long time. And I think it's time to potentially look at things like the dynamic changes in the soil values of how the water goes through it. The permeability may not be static. And it's definitely not static, from a long basis in a basin. So as the saturation increases, how is that impacting the permeability of the soils? How is that impacting the losses? And I think we experienced that this year. I think since we're doing things that are outside the calibration of our normal statistic range, we're coming down in there. Okay, what's really happened physically? Where the soils are thirsty, the evapotranspiration is higher. The runoff efficiencies are going down, as others have noted. So yeah, that's going to impact our results. And do we have a handle on the physical characteristics to try to simulate that, from a runoff model? I don't know. I think we do our best, but that's where the errors come in. Is we need to get a better handle on some of this stuff. Here's some HMS components. Most of you know how this kind of works. For example, this was looking at the soil moisture and what happens and how it reacts. Standard stuff. I want to say that this is consistent with the Sustainable Development Goals of the UN, and specifically number 6, clean water and sanitation for sustainable management of water. But more importantly, what we do actually impacts a lot of other sustainable development goals, either directly or indirectly. And when we do this kind of work, sometimes it's important for us to realize how important this is to people on Earth and a lot of others that actually are dependent on the environment. And it really gets into a lot of other things. Out of this, I think the snowpack simulation with ASO Inc data is important to integrate into our physically based models, and all these other things. I think that's one of it's going to make the biggest difference. We think of H2O as fire on steroids. I think that was somebody told me that. One of my managers told me that. Yeah, Marco, what you're doing is like fire on steroids, and that stuck to my mind. So I'm going to keep saying that. In conclusion, I think that data will be beneficial and a critical component to develop a real-time automated HMS model for the San Joaquin Basin. I hope we continue with our research and all this development, because at the end of the day, we got to put this data to good use, and somebody's got to make a decision. And without that utility and that benefit to all our stakeholders and users, then it's just data and exercise. It's worth millions, by the way. Somebody asked that question before. I've done analysis just alone on power generation, for example. We're not talking hundreds of thousands, we're talking millions of dollars per year. So it's very valuable. That's all I got. Thank you. Appreciate it.
Great. Thanks, Marco. That was great. Okay, we're going to move on to, I don't see any questions, so I'm going to take the opportunity to move on to Greg Stock. He's been working with us for a while now. We've been surveying the glaciers every summer, and So Greg with the Yosemite National Park, he's going to talk about the glaciers.
Okay, unmuted. Can you see my screen?
Yes, loud and clear, and we can.
Great. Okay, thanks everyone for sticking around. I'm going to talk about how ASO data has allowed us to build on a long tradition of monitoring the Lyell and Maclure glaciers in Yosemite National Park, and specifically how we've used those data to reconstruct historical volumes of these glaciers, allowing us to get a much better handle on, I guess, how little ice remains. So to remind folks that don't know, the Lyell and Maclure glaciers are at the headwaters of the Tuolumne River in Yosemite National Park. Tuolumne has been a big focus of this workshop. And as Kat mentioned, this is sort of the OG location for ASO data with 9 years of data. So we've got a nice long data set to work with there. And of course, these glaciers are changing as glaciers throughout the world are. And a big part of our work has been to document the demise of these glaciers and continue the research that began in 1872 with John Muir's first scientific observations of these glaciers. And so building on maps and photographs and data that go all the way back to 1883, we have a pretty good handle on the area change of these glaciers through time. And I'm showing that in map view and also in that plot on the right. So not surprisingly, the glaciers have retreated a lot since their little ice age maximum positions in the late 1880s. And by area, the total area lost for the glaciers is about 78%. In other words, they've lost 78% of their 1883 volumes. But we have reason to think that the volume changes, which is to me really the more important number, might be a little different because each one of these patches of ice up there has a real different shape to it. The Maclure Glacier, for example, is relatively thick compared to its surface area. So after tracking area for all this time, I've, beginning around 2012, started thinking that it would be much better to know the volume history of these glaciers. And of course, the ASO data beginning in 2012 has allowed us to quantify the volume changes over the last years. And that's been super useful, but there's still two things missing. One is what's been the full historical volume change since 1883, and also how much volume remains. And it turns out that the LiDAR data allow us to answer those questions pretty well, we think also. So in the last year, we spent a lot of effort reconstructing historical ice surfaces for these two glaciers. And we use a lot of data for that, including landscape features that you can map in the field, things like moraines and trim lines, tons of historical photos that we have going back to 1883, historical maps and surveys also going back to 1883, the ASO data from 2012 to last year, as well as field-based GPS surveys and satellite imagery. So we've utilized all of these data sets to one extent or another. Here, for example, are just a few of the many historical photos that exist for these glaciers. I would say that between photographs and maps and John Muir's survey, these are arguably the longest studied glaciers in North America. We've also, as I mentioned, done a pretty good job of reconstructing the historical ice surfaces in 2 dimensions, right? In these cross sections that were established in the 1930s, and you can see the glacier surfaces coming down along these cross-section lines. So integrating all of that and using the 2015 ASO data as a baseline, in the digital realm, we reconstructed ice surfaces for a bunch of these historical periods. And we start with the perimeter of the mapped glaciers at that time, which is a 3-dimensional perimeter. And that really helps us out because that perimeter in 3D space actually puts some very tight constraints on what that surface is going to be. For example, if it's sort of the rubber sheet thing, you could just snap it across and fit every point along the perimeter across the range of elevations, and you get a pretty good initial fit. So this is an interpolation of points along the margins and across the glacier surfaces. So that's sort of our first stab at generating these ice surfaces. We can then convert that to a DEM. So for example, this is a DEM of the Lyell Glacier as it probably looked in 1883, right? If you could have made a DEM in that year, it would have looked something like this. But then we use the historical photographs to fine tune this a little bit. We can actually move points on that interpolated surface and get them to match these historical photos. And I think we've done pretty well. You can judge for yourself, but here's the modeled ice surface compared to a kind of a famous glacier photo taken by G.K. Gilbert, famous geologist in 1903. Here's another view of the east lobe of the Lyell Glacier in 1883 and the modeled ice surface for comparison. So in general, we think that these modeled ice surfaces fit pretty well. And from that, then we can reconstruct these historical ice surfaces for each year where we have really good photos or maps or some combination of that. So just to walk you through this, this is a view of the modeled glacier in 1883, 1903, 1931, 1944, 1955, 1972, 93, 2003, 2012. We actually have real data for these volumes, but I'll just show you the modeled ones and tell you that they fit the calculated volume changes quite well. And this is in 2018. So with those reconstructed ice surfaces, we can then difference, say, the modern glacier period, the modern glacier data against the 1883 surface. This shows you spatially the change in glacier thickness across those three glaciers. So in many places, we're seeing up to 75 meters of ice thinning between 1883 and 2020. And the final piece to the puzzle is to get the absolute volumes for these glaciers. And there is still some ice remaining. So the way we need to do that is to model what we think the bedrock surface looks like underneath the remaining ice. And again, the LiDAR data has proved useful for this as well. We start by creating a bunch of cross sections that we think are fairly realistic for what the bedrock should look underneath there. From the cross sections, we then generate a 3D surface. So remember, that's the surface that we think exists underneath the ice. And last year we did a little bit of ground truthing of this using a steam drill. And that photograph on the right shows Lee Vining High School student Ellery McQuilkin, who I've been mentoring on glacier studies. She's just an amazing young scientist and super motivated. So she carried the steam drill up to the glaciers, and in a number of places on both the Lyell and Maclure glaciers, we used the steam drill to drill holes down at least 13 meters. That was the maximum amount we could go with the hose. So we're kind of along the margins of the glaciers. And in general, our modeled thicknesses matched, at least along the margins, the measured thicknesses pretty well. So overall, we feel pretty good about this. And once we have the subglacial bedrock surface, we can do sort of the full ice volume estimates. Here you can see we're looking at something like 47 million cubic meters of ice in 1883 in those three glaciers. And just for perspective, I know there's been a lot of talk about acre feet of water. That's like 34,000 acre feet of water, roughly 13% of Hetchy's volume. So we're talking trivial amounts of water here, especially more recently, right? This is the cumulative ice volume for 2020, more like 5 million cubic meters, or about 1% of Hetchy's total volume. So in terms of the amount of water, especially now that's stored in the glaciers, it is almost nothing compared to even a poor year of snowpack. But it is still really important when it comes to the runoff, which is, I'll mention that in just a minute. But when we then compare the area losses that we've been mapping for quite some time with the volume losses, we do see that it's not necessarily a linear relationship. There's been a 78% decrease in total area, but converting to volume, we see there's been roughly a 90% decrease in total volume. So we've actually lost more ice than just the pure area analyses would suggest. You know, we can do regressions, and we have done regressions on these data to come up with an estimate of when the glaciers will disappear. It actually varies a fair bit for the three different lobes, Lyell East, Lyell West, and the Maclure Glacier. The Maclure Glacier is probably going to be the one that sticks around the longest. I might give it 40 years. Lyell East, I would probably give it 5 years, and Lyell West would be somewhere in between. But I want to say that because the glaciers are so small now, they are becoming extremely sensitive to an annual year of precipitation. And that's not the way we typically think of glaciers. I mean, glaciers are some of the best indicators of climate change because they're kind of buffered from that annual variability. But because these glaciers are small and because we're having quite variable precipitation from year to year, I might say that the east lobe will be around for 5 years, but if we have 2 or 3 years of well above normal snowpack, that will insulate the ice from melting for like 4 or 5 years at least. So it's getting difficult to make the final prediction of when the ice will disappear, but that's a function of there being so little ice there now. And just to reiterate that point, I took advantage of the good air quality 2 weeks ago and ran up to the glaciers in a day and just took some repeat photographs so you can see here's the state of the glaciers as of 2 weeks ago compared to 1903, for example. Not a lot of ice left. And then the final point I want to make are just what some of the implications of glacier loss are for the uppermost Tuolumne River. And here I'm showing you 2 hydrographs for 2013 and 2014, so during the last drought years. And we're looking at the tail end of the hydrograph. So we're really looking at the conversion or the transition to base flows. And that gray shaded area is when we're looking at primarily glacial melt. There's 2 lines there. The lighter blue line is the Tuolumne River as measured at the road bridge. So near the Tuolumne Meadows campground. So in Tuolumne Meadows, basically. The darker blue is measured at the confluence of the Lyell and Maclure creeks on the Lyell fork of the Tuolumne River, so just downstream of the glaciers. And the point I want to make here is that we see a convergence of those 2 hydrographs, indicating that during the late summer and fall of these drought years, something like 75% of the base flows in Tuolumne Meadows is provided by glacier meltwater, right? So 3/4 of the flow that you would see in Tuolumne Meadows this time of year, and potentially right now, is a result of melting of glaciers. So again, the overall volume of this water is really small, but the buffering effect is large. Without the glaciers, I would think that at least parts of the Lyell Fork would be looking dry, would be subsurface flow. And again, this is another year like these years where that's been really important. So this is a photograph of the Lyell Fork during one of those dry years. Really the only source for the water that you see this close to the glaciers is the glacier melt themselves. And once the glaciers are gone, that will be a different system for aquatic and riparian species. So that's kind of where we're turning our focus to next. I think it's lunchtime. So I'll leave it there. Thanks.
Wow, that was amazing. Thank you, Greg.
Yeah.
I want to say a couple things. So, hey, Greg, thanks so much. I want to tell everybody that who is not familiar with that short jaunt into the glaciers, that when he mentioned he went in there for the day, it's about 13 and a half, 14 miles to the glacier one way. So, so we owe him a debt of gratitude for a cranking day of 25, 26 miles. And also, I just wanted to let everybody know that when we founded ASO Inc, we made a commitment at that point that we're going to, every fall, we're going to fly the glaciers of California and keep this record going. So it's going to be on ASO Inc dime to preserve these data going forward and to be able to provide that history of their demise, and to work intimately with Greg on and other scientists as well on the analysis of those data and seeing the educational programs to carry those forward for hopefully centuries to come, and hopefully into a time when we can regrow glaciers if we get our carbon issues dealt with. God, there was one more thing I wanted to mention. I can't remember, but I'll stop there. Thank you.
Okay, great. I'm gonna honor one of these questions because I'm interested. Gabriel Lewis asks, have you used any ASO photos or LiDAR or GPS to do feature tracking to see if there's any glacier flow today, or is the ice totally stagnant now?
Good question. We've played around with tracking a little bit, but again, these glaciers are really small, and you kind of need at that scale, because the glaciers are small and the movements are relatively small. We haven't been successful in that, but I don't claim expertise either. So we'd be happy to get some help with that. But I will say that we've measured these glaciers in the more traditional sense using stakes. And when we did that last in 2012, which was 140 years after John Muir's experiment doing that same thing, we found that the Lyell glacier had basically stagnated. It was not showing any movement at all, probably because it's so thin. And somewhat oddly, the Maclure glacier was moving at about 7 meters per year. And during that late summer period when Muir measured it, we were measuring it at the same rate that Muir did. So it was like 2.5 centimeters a day. That's not necessarily a sign of health, because I think it's a combination of a much steeper ice surface and more meltwater at the bed that's allowing it to slide faster. Next year marks 150 years from Muir's experiment, so we do plan to do the stakes again. But if there are virtual ways of tracking the measurement, I would definitely like to pursue that too.
That's great.
So, Jeff, do you want to take us away with the with this ultimate discussion for the workshop? And likewise, we'll have everybody throw in thoughts that you have, and discussion points, etc.
Yeah, please do. Sorry, I'm buried in Windows here. Let me extract the proper ones. Why Zoom insists on bringing that like general window to the front all the time, I don't know. Okay, for for our last discussion here, we don't really have a topic identified for today's discussion, and I think that was a bit intentional, mainly to allow for a bunch of different threads to be discussed that may not have been captured in the past couple of days. I have a few ideas, but as before, I want to encourage folks to contribute to the discussion. Post in the chat and Q&A if that's your preference. We'd rather you speak, so go ahead and raise your hand. We can unmute you and you can contribute. So a couple of topics that I'd like to discuss hinge on some of the some themes that Steve Haugen talked about this morning, and that some of our team just described a little bit of things that we're changing, and that is the under the broad topic of communication, but specifically data delivery and some of our web-based data exploration, exploitation, software as a service development. We have, I guess I'll little monologue this a little bit here, just as by way of background. We have such a diverse set of collaborators and stakeholders that building, well, there's two challenges with building what we're trying to do. One is that you'll never be able to satisfy everybody's needs all of the time. And the other is that we're doing something that's fairly new. So asking all of our collaborators and upfront what they want out of our data system really doesn't get us very far, because everyone says, you tell us. So that's what we've been doing. We're telling you what we're doing, and now it's time for some feedback. So so specifically what, we've been rolling out some new graphics this year that Kat showed, and you've seen dribbled throughout some of the different hypsometrics, elevation SWE curves, and comparison curves, as well as our what we like to call the HAL plots, because they look like the evil computer in 2001. But those elevation aspect rose diagrams, or cone plots showing the distribution of SWE or the distribution of changes in SWE with aspect and elevation. We started doing elevation plots with snow albedo and the 3 different albedo components. All of this falling generally under, distilling the data in hopefully useful ways so that those of you who are consuming and putting the data to work can extract something meaningful out of it. So we've started doing, basically the straw person, putting something out there that we think is useful. And then Evan and Jacob showed some of the development that we're doing on the web-based tools, allowing exploration of our time series of data, as well as asking some specific questions of it. Again, we've identified, based on our own experience, some useful ways to do that, but would love to hear from other folks out there. And honestly, I think this can be a broader discussion as well. We'd love some feedback on our stuff, sure. But this broader topic of communicating technical results to engender action or decision support information is one that there is no one answer to. It's a panoply of answers. And just looking at our attendee list, I see lots of experience with that kind of thing. So would love any comments there. Anybody itching to talk about those subjects?
I'd also just say that even if people maybe might not have specific suggestions as to ways that we could improve the software, the more that we can understand how, in a very literal sense, how these decisions are made and how the software may or may not impede that process. In the literal sense of, I decide I'm going to do this, then I print up these plots, then I go talk to this guy, and I have to convince him, and he has a thick skull, and I have to get that through him. Like, trying to understand that level of the process can at least get us to see if our software is doing the right thing or not. If no one says anything, do we just
I'm wondering if having everyone muted is working here.
Yeah, then we start calling on them.
I was just about to start threatening that.
Yeah, one raised hand.
Oh, Pat Hayes.
So in the software discussion, the product was being delivered, albeit in a very labor-intensive overnight function in a 24-hour turnaround. Everybody seemed to be happy on that from the receiving end. It was a nightmare from the delivery side. And now we're typically in about a 72-hour turnaround. Is that all still correct? So what would be interesting to hear is what is the criticality of getting data sooner than 72 hours? And is there a method or a madness that can get that if such a customer has that need?
Who wants to field that? You want to field that, Kat? I can speak to some of that, and if Kat, if you disagree with me, a lot of the pipeline has been very much accelerated, and I think by next spring we're going to be speeding up a lot of the other aspects of the processing. In a lot of cases, the 72 hours has been a time that we have needed, specifically Kat and her team have needed to go through and just make sure that everything is working and looks good. We don't want to, with automation is great, but we don't want to just blindly send data off to people assuming that it's all good and big decisions get made. So we want that time to look at it and make sure it's good. A lot of the stuff that we were talking about, improving calibration and so forth like that, is going to really help our confidence and make that process of Kat giving it her stamp of approval that'll make that process better. And so I think that's is in my opinion, it's like as we grow and gain more and more confidence about the reliability of the process overall, that's what's going to start bringing down that.
And I think
72
Pat was
hours.
also poking the other direction at the end users, like how many of them need or would like to see it quicker, sooner.
Yeah.
Yes, I was.
So I'm sure one of them will. say
Everyone's saying it's last day.
Oh, is everyone waiting for me? Oh shit. Well, yeah, no, I was poking both ways. Really, how quickly do we need to get these things out, and what's the most useful? But then realizing that having that little bit of extra time does give us more time to really go through the data and look at it and make sure that it makes sense, and not just from the snow depth, comparing it to things and sort of dancing around the basin, but also looking at the hydrology and, does the runoff that we've seen between these two flights, does that kind of gel with the magnitude that we have seen, leave the snowpack? And so having that little bit of extra time, boosts the confidence in non-negligible ways. And it really helps us to deliver the first time properly, just really nail it the first time and not make any mistakes.
And in fact, once we're in full flow, it's not any easier to deliver at 72 hours than 24 because they're all lined up anyway, right? I mean, we get stacked up pretty fast because everybody wants April 1st.
Matt Meadows looks like you might have something to say if we
yeah,
give him a chance.
So I'm being a little bit distracted. We are running a Zoom meeting for my office manager who's retiring after 60 years. So I'm kind of keeping an eye on that Zoom room on the side. So it is you can't teach an old dog new tricks. I had to set up the camera for her and get her onto Zoom, but it was faster than Tom was earlier. So. But the question is about timing. Like, a 72-hour turnaround. I need a 24-hour turnaround. I need a whatever the turnaround is. The question is, it depends, right? If your model has run good over several year types in a basin, so your snow model, for example, you've had a wet year, you've had about an average year, you've had dry year, and it's looking pretty good, so that each flight isn't adding, say, a significant amount of change to that model output. Maybe taking a little bit of time, especially during the ablation period, to make sure that you're getting that melt rate right, is very important. So adding a day, as long as you think you're in a ballpark, plus or minus whatever 5-10% on your model, maybe you can wait a little bit longer. If it's your first flight that's going to make the biggest impact to that model run from the distribution of your snowpack, maybe that one you take a little bit longer to really make sure that it's absolutely perfect. But and then somewhere in the middle, maybe you can have a faster turnaround. I don't know. Does that make sense?
Yeah.
Or if you get a call from me and I say, I have a very, very important decision make and I can't be wrong, and can I take the extra time to make that decision? I don't know. It's almost like a case-by-case basis.
Or even the flip side, like you call up and say, I've got to make a decision tomorrow night.
Hey. Yeah. And I can take a little bit of error. What does the data look like while the aircraft is still running? And I think that really
little
comes down to
box.
how well we think the model is running, because it's that model running in between the flights that gives us a lot of information. And if we have high confidence in that, then and we can make decisions with less information from an actual flight, I think.
Let me add to that. So I think the ideal situation is one in which you you can know when a flight is going to happen and when you're going to be able to look at those products, and we've communicated to you what the uncertainties are and the accuracies, and so you can. We've talked about this over the years, that you'll come to that product with strong confidence, and that can be a big bump in the confidence. Then with the new visualization tools and the modeling structure from M3Works, as well as then the projection further into WRF Hydro, we can have then those model results available on a 24/7 basis, so that you can go in and query that, and you'll be able to have associated with that the uncertainties that you're looking at. But it's not just that you're looking at whatever the window is for the ASO acquisition, that all of those products are going to be available to you, those model outputs, and that you can query them in the way that you desire, with our expression of what uncertainties you're facing at that model result. So if it's been 2 weeks since an ASO update, well, you could be a modeler and say, oh yeah, well, it's perfect. Not all modelers are that way, but you're gonna know that you want to look at that more carefully and be a little more cautious than if it's the day after an ASO acquisition or a day after an ASO delivery. But ideally, weaving these physically based, well-constrained models into the mix with 24/7 availability, we hope is going to help out with that.
So can I flip the question around? As a
Do it.
snow data collector, as part of the California Cooperative Snow Survey, we keep saying, oh, we need fast turnaround from this ASO product, but the ASO product is also reliant on other things that people collect, like snow survey data. And I know that I've been trying to collect and get those data out to the group as fast as I possibly can, knowing that that information might affect the accuracy of my ASO product that I'm chomping at the bit for, and maybe don't want to wait until the 3rd of the month when the final data are published through DWR. Any comments on that?
Matt, sorry, Kat and I were looking at a technical issue and missed what you said. My apologies. So that's part of the reason that we're deer staring at a train.
He was asking about the other inputs that we use and their timeliness. Like
survey data,
like cooperative survey data, other things that we might use as inputs. Are we getting them quickly enough?
Weather station validation data.
I just want to jump in real quick, and this isn't something that we're doing now, but we've talked about using some of that data to correct for known biases in the HER and other inputs that we use. So looking forward, yeah, that's really important. Like as fast as we can get this data available and QA'd, that could make room, at least on the modeling forefront, for some semi-real-time adjustments to the inputs.
Right, and from my perspective, I think the snow density estimates are really useful. So we get them, from the sensors, which we, are usually working, and if they're not working, you can tell pretty quickly with the density metrics there. The snow courses, obviously, they're every month, and so there are times when we don't quite have the information that we would like to do the full constraint, and so we do our best in that situation. The other thing I would say is if we could, like some of the measurements that you went out and took, Matt, and then you feed them back to us directly, that helps tremendously. So I was looking back in one of the reports that we did for the Kings, and I had 20 snow courses, from data from you. And so we didn't have to wait for that to come through. And so that absolutely helps. So, pretty much we'll take any snow density estimates we can get our hands on.
And are we getting those in a timely fashion?
Right, from when they get collected.
Yeah.
Exactly. So any heads up before we have to wait for them to come out on CDEC, that is really useful for us.
I'll mention that, that metadata is kind of critical there too. We're slowly building our library in conjunction with the operators of precise GPS locations on snow pillows and individual snow course measurements, not just the general location of the snow course, but the actual hole by hole locations. Because we can use those to select which of our grid cells it's in and compare the snow depth and density values. And metadata about the stations, like whether the snow depth sensor is co-located with the snow pillow, is critical information as to whether we can actually use that site for density. So this is an evolution that's ongoing, and just got a big download of site information from the Colorado NRCS folks actually just recently, which was super helpful. So that kind of thing is part of it's one of the nuts or bolts that's kind of gets hidden in the background until it's time to actually do data comparisons. So we're definitely dependent on those existing networks. Dave Rizzardo's been mentioning some, I think that maybe Steve mentioned this morning as well, that ASO data can serve as a great either validation or backup in case a station goes down. True, and that's certainly certainly an application. But when we see stations go down, we're just as heartbroken as the folks running operations in those basins, because we've long said that initially when the ASO program started, people would commonly come with the question of, so does this mean SNOTEL's obsolete? And we, from day one have been like, no. We depend on it. In fact, we would argue that the SNOTEL network needs to be doubled or tripled in terms of the numbers of sites out there, because we use them. It may be that we're using those data in a different way than they were originally intended as that network was built out, but that doesn't make them any less critical.
I had a comment earlier that I discussed in chat, but just in general, there was a very good comment that one thing we didn't mention about our new web application is the ability to actually look at the station data on the map and be able to compare the actual station data to what ASO sees. And I mentioned briefly, but the same thing that Jeff was just talking about, the limitations there are just little things like making sure that we actually do know the correct location for the snow pillow, and if snow pillows go awry, that comparison can be wonky. It's wonky. So just kind of we got a few things to sort out, but I think once we get to a good point there, I hope in the future we'll be able to integrate that data in with the rest of our tools.
Dave Rizzardo, and then Carly McClellan.
Well, I sometimes feel like my role here is to state the obvious that everybody knows, but I'll go ahead and keep doing that. Before I do that, Matt snuck in there the reference to Pam there at Kings River, and Matt, please pass along how much love we have for her and everything she did at Kings River. The people often behind the scenes are the ones moving us along. So I apologize, I can't jump on her. 60 years in one agency. Well, I thought Maury Roos.
I just saw Frank Gerke jump in and say hi.
Well, Frank doesn't have anything to do these days, so that's all right. But anyway, this discussion on the in situ network and everything else, and again, just to state the obvious, it's recognizing, what Matt does as well, above and beyond, and greatly appreciated, and certainly vital. And I think this even goes back to what Steve said, where sometimes the managers are looking for that silver bullet, and there's so much potential with ASO, but at the same time, right, it can't also do everything. I mean, we know it can do a lot, but water managers are asking for real-time everything, and unfortunately some of this data just never will be real-time everything. When you manage a cooperative snow surveys program that's dozens of agencies over 250 snow courses, sometimes you're going to get what you're going to get. And so we're working with the Forest Service and the Park Service and all of our cooperators and everything else, and I think by and large they do a pretty good job. But if we ever get to that point where they're all able to produce data and get it in almost instantly, and that certainly there's been iterations of trying to figure out how to do that, that'll be great. But that's just a logistical challenge that it's going to take some time for us to get over. And then the same for the Pillow network. It's, again, I'm going to state the obvious. I think everybody here understands the challenges. In a perfect world, we had all the permits and all the access to do whatever we needed all the time. But really what slows us down is just that. It's even if we had more staffing, it's just getting the permits in place and the access and the tools to do the job and keep it up and going. And then you do all that and a windstorm comes through and knocks it down, or a fire takes it out. So you guys all understand this. I'm bringing this up from that point that there's so much potential here, but there's always going to be some limiting factors. And I think, as Steve mentioned earlier, we're just open and honest with that with decision makers, that there are challenges we have and we can accomplish, and some that are just going to be really hard to overcome.
Hey, Carly, right before you go, Kat just asked me, who's Ed Melcher? Did he just disappear though? Or is he still on here?
I'm here.
Oh, there you are. Hey, Ed. Just hang on, but I was going to tell everybody it's a blast from the past. So Ed was working with Optech, the first lidar provider that we worked with, and he was here doing the data processing, and he's the one that told us that the first flight was all jacked up for the snow free and it had to be redone, and his buddy had to go refly it. So Ed, hang on just a second, and I want to give Carly McClellan the floor. Carly's from the hydrology department of Navajo Nation and a good partner of ours.
Yeah, can everybody hear me?
Yes,
we can.
Yeah. All right. Well, great to hear all the talks, and wonderful to be invited to this virtual ASO. I did attend one in-person ASO way back when, maybe a couple, 2-3 years ago. There's just so much information out there, and it's always just mind-blowing. I always enjoy these. Looking forward to some more in person down the road, when things kind of start to loosen up. But with that said, I also wanted to, look at, Tom, when he was still with JPL, I've been scratching his back, at least, hoping he'd scratch mine back, or we'd work something out and we could figure out maybe some funding for Navajo Nation and have some ASO out here as well. And so we've been trying on our end, and it's like, we've come close a few times with the Katina Foundation. And so still definitely there's a huge interest in at least on my end, from Navajo Nation side, to continue pursuing ASO. But I guess the question I have is that, being from, just the outside looking in, just peeking in through the window, so to speak, of ASO usage and actually using the data set for our daily needs, I feel like I'm just kind of just looking in through the window, kind of just wishing at this point, but with that said, kind of looking with some possible planning. I know that Jeff and Tom, they've been kind of in contact with me with possibilities of no snow flyover funding and maybe other funding that might become available through the BOR and in the near future. So, if those things do, at least, find some substance and funding from our end, I'm looking at maybe just some questions about software needs. Are there any specific types of software I need to plan for, or servers, or something that I would need to purchase in the event that down the road, we, from a planning and visionary standpoint, when we, let's say all things align and we get funding and we start getting ASO flights and ASO data, I'm sure there's probably millions of data points. And so I don't know if all of that would be on like a cloud or how that works. And so, and I don't know how other stakeholders are managing that data, if they're using that data on maybe on their own internal servers. So kind of just looking to try to see what I would need to do. Are there things I need to invest in for like a cloud database of some sort, or some type of a server network that I need to house the data on, or specific types of software. So that's kind of where I'm coming from. I just wanted to know what everyone's input was, and with regards to ASO data management.
So Carly, that's it's a great question, and it's one that we've been putting a lot of effort towards solving. Well, I'm saying solving for some customers, and I think like yourself, who don't necessarily have the infrastructure set up immediately to be able to ingest, analyze, store, and produce figures, and then actionable information and actions. The tools that we've been working on with ESRI are designed to do exactly that, and it'll be great to have a follow-up conversation with you on that, just to walk you through where we're planning on going with that over the next few months, and make sure that it attends to what you're after. And our plan is to bring the software to a certain point, and then have a meeting with the various customers to get their feedback on what's missing, what's redundant, what's unnecessary, and quite simply how we can make it better for you. There were a few customers in the Central Valley of California who we talked to about what we were building, and they said, "Oh, thank God you're building that. We had started working on something just like that, and we're gonna hit the brakes and wait for yours, especially given that we get to provide input on that." So,
there's also a variety of open source things out there now, like QGIS and other things, where our products are going to be in generic formats so that depending on what kind of GIS setup you have or don't have, it could be quite inexpensive to at least ingest the stuff, do simple calculations on it with open source software as well.
Right.
I mean, a lot of our intention with this, with the application we're building now, is that you should be able to make the basic decisions that need to be made with just a laptop and a web browser. And if you want to download the data and get used to your, play with it yourself, as Joe's saying, there is free software you can get online to work with that, and that's the first step. You don't need big servers or any major hardware. All that problem is stuff that we are dealing with for you guys, so you don't have to. Yeah.
So Carly, we're not quite ready to roll it out to a hands-on demo and a breaking of it session and a discussion, but that is going to be coming up. But I think given where you're at right now, it would be great to have an offline conversation with you about what your needs are to be able to take action off of your hydrologic data, and we'll be doing that with others. Does that address what you're wanting to pursue?
Yeah, it does. And thank you so much, everyone, just kind of for all your input. And Joseph, thank you for suggesting the free open source options as well too.
Yeah, we look forward to flying there. So
yeah.
Yeah, great.
Yeah, we are not going to give up on that. I mean, we were getting very close on a couple of fronts, and I think we're still headed in the queue to ultimately get that going. And so I would love it if we can show some results of some form, either snow on or snow free by next year's workshop. Fingers and toes crossed. So Ed, you got an introduction. It's great to see you sort of hear you again.
Yeah, I was gonna say it's a long time. I think if I'm not mistaken, it was a drive from Grand Junction to Mammoth Lakes, and you were talking to Mackenzie about her PhD.
Yes.
The whole way. So
that's right.
It's about how long ago it was.
13.
Yeah.
On the extraterrestrial highway.
That it was. So I'm the LiDAR guy, obviously, so I'm kind of always curious about the application and what has learned over the years. Like, has the new technology, because I mean, like, you went from like an Optec Gemini now to like dual lasers, cross action to help penetrate certain cracks and stuff that you couldn't get on the first renditions. Like, has that led to an increased precision in collecting the volumes of snow, or is the LiDAR like getting better, just been kind of the same throughout the years, or any lessons that you might have learned in the base modeling?
It has I'm going to give an answer, and then I'll defer to Jeff and Kat as well. But I think first order, it has allowed us to fly higher and faster with even greater fidelity of measurement than we had back a decade ago. But those advancements that happened a decade ago really pushed us over the threshold to be able to do what we do now. Fly entire basins instead of flying 100 kilometer areas, actually being able to cover those basins. Now, I don't know if you remember, but it would usually take a day and a half to fly the Tuolumne, and it was 50 some odd flight lines, and it was just the Tuolumne and just the smallest part of the Tuolumne of Hetchy. Far more than double in just a few hours, and picking it up with the Merced Basin and part of the San Joaquin So any rate, I think Jeff and Kat for their input. Jeff, go for it while Kat and I switch audios here.
Yeah, I mean, I'll expand it even bigger. The ASO wouldn't have been possible had we started probably even 5 years earlier, certainly 10 years earlier. The advance in LiDAR technology has been so rapid recently as to make this full watershed approach possible. And so Tom described just the advance that's happened since we started flying. If you go back an equal amount of time, you know, we wouldn't have been doing full watersheds at the kind of scale we're talking about. So we've been able to increase our scope while maintaining or even improving our snow depth retrieval accuracy. And there's some other advancements beyond just the technology. We work really hard on relative registration, for example, and that's a key to any differencing technique, of course. But those have been, sort of an iterative process enabled by the technology. Our technology application is then enabled by our software and software development and applications work, and vice versa. They kind of feed on each other. So we're benefiting from this zeitgeist of LiDAR technology and processing applications development that's ongoing. Kat, anything to add there?
No, I don't really have anything to add on that. I think you two covered that really well.
Ed, is there anything coming in the LiDAR world we need to know about?
Other than potentially when flash LiDAR is going to be the mainstay. That'll probably be your next big like collection efficiency, but that's still a ways away, especially in vegetation because it's a noisier platform. I think you're probably going to see like instead of 2 lasers, 4 lasers, 4 lasers, 8 lasers, just all kind of shooting off in different directions. It's probably the most likely and probably best scenario for you guys.
We like more lasers.
I like more lasers.
I've lost lock on all of our chat and Q&A. What am I missing here, folks?
I see that Steve Haugen has returned post meetings and pre-party. But he's probably all talked out today. Oh, there he is.
I'll bring up a question that is not in my purview, but it's a question I've been asking after hearing about Colorado more. Is so if we have 2 planes within a year, maybe 3 in a year, but it sounds like within a few years we could have a lot more stakeholders, I'm forgetting who was speaking a couple days ago about the number of stakeholders in Colorado, but I'm curious about how can we best schedule all of this and hit time points that people want when we have so many different stakeholders with various interests.
Yeah, I'll
it's
add
purely
to
a
that.
non-scientific practical question.
Yeah, it was probably Lorna Cates talking about that, and we Matt's suggesting a doodle poll. One of the things that we being the Colorado ASO program now, not just ASO Inc, are asking for feedback from stakeholders on is exactly when data is most relevant for decision support. So not, kind of inverting the problem, not when, how long to from flight to delivery, but when should we be targeting? Now, obviously, there's vagaries of weather and other scheduling issues, but when should we be targeting to get data out so that they're maximally relevant for specific operations? Some of those operations are a little flexible when they can make decisions. Others have a hard deadline, like this decision gets made on this date. And there can often be nested sets of those types of decisions within a single basin. So it can be kind of complicated to try to meet all of those needs. But that's one thing that we're trying to build through the stakeholder network in Colorado is a broad awareness of all of those different timing needs.
Yeah, just kind of kicking in on that one. I just even look at adjacent basins, just a comparison between the Kauai and Kings. The Kauai's peak runoff is 2 to 3 weeks ahead of the Kings. So there's a priority, just between those two basins, there's a priority of timing when Kauai would run their flights versus the Kings. Likewise, I'd expect that to probably flip around at times where we need a bigger priority on the Kings at that point. And I think that's where we start looking, that's where that local cooperator network and coordination will be key, is sorting those types of things out. Then overlying the weather and availability of aircraft and all those good items.
Right, and that's where our participation in those meetings is required, just to provide the logistical understanding. But yeah, the cooperator program in California, and I'm psyched to see Frank having raised his hand and getting on here to be talking permitted. It's such a fantastic model for cooperation and for data sharing, for information sharing, for idea sharing, and likewise, just watching the way that the committee that the DWR helped to organize with the cooperator program specific to the ASO program is just it's so great to watch that and to see these people getting along well, so I think it's a great model for what goes on in Colorado, what's going to go on in Wyoming, and everywhere else that we expand. And in the cases perhaps of other nations, there may not be as much sharing between basins, and so there'll be an interesting twist to that. First and foremost, what goes on here in the Western U.S. is one of data sharing and assistance and cooperation. Hey, Frank, can you unmute?
I think I'm unmuted.
Now, before you say anything, I just want to make sure that everybody that's on here knows who you are, since you're a bit retired and less visible now. But this is Frank Gerke, who since 65 million years ago was the head of the California Cooperative Snow Survey Program, and also was the person that let you know where you could get free coffee anywhere. But really, Frank was the one who in 2011 I called up when JPL had given the go-ahead for building what was to become ASO, and I said, "Hey, Frank, here's what I'm getting the opportunity to build with this awesome team. What do you think?" And fortunately, we had a good relationship, and it enabled that door to be open. And Frank brought us together with the operational community, along with Bruce McGurk. in a way that wouldn't otherwise have been possible. And so, any rate, he also helped to bring the water bond funding for the first 3 years of the ASO program. So about a third of the program was paid for by DWR and 2/3 by NASA headquarters. And he and I were the Frank and Tom show on CNN and New York Times and on and on. So any rate, Frank, welcome back.
Definitely. Hope to see you in Mammoth sometime this fall.
Absolutely. So what do you have to say about the program?
I am very impressed at how rapidly it's expanding and how seamless it has seemed. Now, of course, I'm not on those late night emails wondering about why the data processing has, hung up on a particular flight line and all of those issues. But there seems to be less of a panic than early on. And I think in part it was a relaxing that 24-hour turnaround time.
Yes.
We could put you on the email list, Frank.
That's okay. I don't need to suffer those anxieties anymore.
They call it Slack now, and it never stops.
But it's very encouraging, and especially with Dave Rizzardo's efforts to expand the program into other basins within California, and how critical that's going to be going forward, considering how much of some of the sub-watersheds have been completely burned over. I'm thinking in particular the Dixie Fire and how that is going to probably very dramatically affect the timing and volume of runoff, assuming we get snow next year.
Yeah.
And I think it's, it's unfortunate we're having, these wildfires, but I think it is also an opportunity to demonstrate the value of an updated examination of these watersheds.
Frank, can you see that your interaction with the governor sampling no snow is up on the screen?
I can. Yeah, that was one of the more panic-stricken days in my career. I was unsure what Roy, who was a property owner, was pretty kind of a backwoods kind of guy, kept a shotgun leaning against the back of the door. And fortunately, he had no ill will towards the governor.
Despite being nicknamed Moonbeam. Yeah.
Yeah.
So is Dave?
I was going to say, I think Jerry, he in his earlier incarnation as governor proposed that California launch its own satellite. So he had a kind of a forward-looking aspect that I don't think is currently available in the upper levels of our state government.
Well, I just want to say, Frank, that this to me was one of the most effective science communication moments of all time, and one that we see some parallels with some of the data that we're producing, but I think there's nothing more effective than saying, with your colored tape there on the snow tube, saying, look, we're up against it this year, with this kind of imagery. That was to me kind of a watershed moment, if you will.
Yeah, and that's exactly, if we had even a dusting of snow the governor would not have shown up. He wanted that visual of no snow at all, and having that unprecedented dry meadow as a backdrop was key to his messaging for that time.
Yeah.
It just occurred to me that if we ever established a Snow Surveys Hall of Fame, we would need to collect that tube, Frank's jacket, and the podium to have as a, an item in the museum.
Have a whole diorama.
And a clean copy of The Onion with Frank on the cover and the headline reading, California officials assure residents there are more natural resources to waste.
Which I thought was a classic.
Oh God.
So this last year they inquired about recreating that scene. They actually said, well, can we go up there and show, videotape the empty meadow of snow? And we wrote back and said that would be fine, except for there's actually a few inches of snow on the ground. So they instead chose the dry lake bed of Lake Mendocino, which was great because then there was a goose in the background, like stealing the attention the whole time.
So, all right. Well, we're coming to a close, and are there any more pressing comments before I give just a few thoughts to close it out? All right. Well, first of all, I want to thank the ASO team, and in particular Liz, for coordinating the workshop. She's done an amazing job. This is 2 years in a row of doing fully virtual, and it is not easy with this many moving parts. So thank you for that, and for the whole team prepping and being present the whole time, except for Dan when he was off showing off parts to his mother-in-law. And then of course to our keynote speakers, Dave Gotchis and Steve Haugen, and putting the effort in to bring in that vision and really helping us to look forward to for the community, and likewise for us as to what our marching orders are, to be able to achieve those dreams, and to allow you to be out of work and just let a robot do all this, and ultimately for this to be so beneficial to the civilization that we've established out here in the Western US, where we've found ourselves in kind of sketchy times. And so the other thing I want to speak to is just the remarkable expansion that the community has brought, and either in the science that they're carrying on, the operational analyses, which haven't been a part of the operational job, but so many of you have put in extra work trying to figure out how best to bring ASO to full fruition. And likewise, what we've seen in this workshop with the modeling that's been going on, which is really that final step, as Gus Goodbody has brought up pretty much every ASO workshop that he has attended. Awesome, that's great. You got those snow products. All right, let's get on with the real work, and let's get the modeling done with those and other products. So it's so exciting to see what is being done right now, what's already been done, and how much closer we are to realizing that vision specific to snow-covered mountain environments. The other thing that I was struck by during this workshop is the amazing diversity of scientists and engineers that we have here. And if you go back 50 years at the Western Snow Conference, the diversity was just in how much hair you had on top of your white male head. And now we have remarkable diversity in this community. And I think next year, my plan is to invite as many high school and junior high science classes to come in video, not to come to the meeting in person. That would be too crazy. But for them to come and see what is going on and to find themselves there in the cadre of scientists and engineers and practitioners, and to see what kind of careers are available out there and how exciting this can really be. Finally, I want to point out, I actually was going to look up the dates, but I didn't remember to do that. But the California Cooperative Snow Survey annual meeting is coming up, I think, in early November. Dave, do you have the dates off the top of your head? November 3rd through 5th, there it is. And I think it's also going to be virtual again this year. And likewise, they did a great job last year with their virtual workshop. The Colorado River Water Users Association meeting is coming up in Las Vegas in the middle of December. And some of us will be there. The International Snow Hydrology Workshop is coming up in February in Grenoble, if I remember right. And the way things are going, that may be virtual as well, or may even get postponed. But at any rate, there's a lot going on, and from the ASO community, we just want to thank all of you for being such an amazing group of colleagues, and helping to continue to motivate us to do the very best that we can. And I'll tell you that the team that we have here at ASO Inc. Get emotional about this. You've seen the expression in the chat and the Q&A, but I can tell you behind the scenes that they are every bit as enthusiastic about it and what it is that they're doing and being able to partner up with you. So with that, I forgot a gavel or a boot to close the meeting, but consider the meeting now closed, and we'll be talking with you soon. Thanks, everybody.
Thanks all.
Thanks, everyone.
Thanks.